So I decided first to review ray tracing of lenses because you covered that material like 3 months ago, right? And I'm planning to ask questions only about converging rays, converging lenses, lenses, right? Because diverging lenses, yeah, slightly more difficult, and we don't use them very often in our work, right? Most of the time converging. So first, ray tracing. Right. It's almost like a review. Instead of this, I decided to review it kind of separately. Okay, and as I said, first about converging rays, lenses. Right. So, of course, you remember you also use the formulas. I'm not planning to ask to give problems about the formulas. I just want to see your ability to draw those rays to find the graphical position of the image. And in order to use those rays, you need to remember 3 typical rays. So let me draw them. So 3 situations. So let me first draw them like this. So this is the optical axis. Then let's say this is the lens, right? And when you work with any lens, you need to remember about 3 special points. 2 foci points or focal points. Let's say this is first, this is the second F, and the center of the lens. So those 3 points. And we're going to use 3 rays, and each time, each of those rays must use only one out of these 3 points. So the first situation, how we usually when we were kids, right? How did we use lens? I know you wanted to set on fire something, right? At least my childhood in 80s, right? So you would focus the sun energy of the sun into one spot in order to set the fire on something, right? So essentially, you have from the sun you have a bunch of rays parallel to each other traveling. That's how we model the radiation from the sun. And of course, then all these rays will be focused at one spot, which is called the focal point, right? So after the lens, they will all go through this focal point, right? So this is the ray number 1. Ray number 1. If before the lens a ray goes to parallel to the optical axis, after the converging lens, it must go through the far focal point. Again, usually just focusing the sun. That's how I call it this case. So case number 1, focusing the sun. Okay, sounds very fancy, focusing the sun. Sunlight, of course. Okay, so that will be ray number 1. Now, ray number 2. Let me again draw the lens converging. Again, the same 3 points. So you see, ray number 1 uses far focal point. Then now, let's say these are again our 3 points, F, F0. Case number 2, it's basically what if you reverse in time these rays? What is going to happen if you reverse? Instead of sending ray like this and like that, what if you send it back? Yeah, no. First, you send it through the focal point. Then, after the lens, it will go parallel to the optical axis. A reverse in time situation, and you will get the ray number 2. But you need to draw it on this side of the lens. So, if you send the ray through the focal point, the lens will send it parallel to the optical axis. So very often this trick, reversing time, is used in order to analyze the physical situations. I remember my advisor when he was teaching lasers and applications. I remember at some point he used that. I still remember. Okay, so reverse situation. So if you send a ray through the optical focal point, after the lens, it will go parallel to the optical axis. Okay, maybe even let me write it so it's an optical axis. Right. Okay, so this is the ray number 2. Ray number 2. So reversing case number 1. Right. Okay, in the last situation, so now you see ray number 1 using far focal point, ray number 2 using near focal point, and now, of course, for the last situation, of course, that ray will use the center of the lens. Okay, so the last situation, so again, let me draw the optical axis, and this is my lens. And so, again, 3 points, F, O, F. So the last ray is trivial. What if you send a ray through the center of the lens? At the center of the lens, essentially it's a slab material. There is no curvature. Slab material is not going to change direction of the ray. So it will go straight through the center point. It will just go through straight like this. So this is the trivial situation. So, and it uses the center of the lens. So case number 3, trivial. Okay, so now using these 3 rays, we can draw and find graphically position of any image. So let me look at 2 situations. So let me put a new bullet. And first, and every time, 2 typical situations for the converging lens. You can position object outside of the focal length and inside of the focal length. So in front of this F or behind this F. So there are only 2 situations, nothing else. Okay, so now let me, so what if an object before the focal point? In every time on the diagrams, we draw an object on the left side, right? Sort of in front of the lens, right? So for the sake of convenience. So before the focal point, right? So now let me draw the optical axis. Right? So then let me draw the lens. Okay, decent. Then 2 focal points. Where should I draw them? Maybe over here, 1, of course, the center, and distance must be the same on this side. So it's F, O, F. So converging lens. And let me position my object, as I said before, outside of the focal point. So let's say somewhere over here. So that's my object. I usually draw like an arrow. Or you can draw something in a... When I managed to get to this material, I would use some Christmas tree, some cats. Okay, so now let's find the image graphically. Where are we going to get this image? I'm going to use all three rays, but of course you understand even 2 rays are enough in order to find position of an image, right? So because every time image will be at the point where those 2 rays intersect each other after the lens. Okay. So ray number 1. So first of all, of course, all this, if you take, for example, the top of this object, of course, it creates rays which goes in all possible directions. Just in nature. Right? Of course, it reflects light because although you can make that as an active source, you can position, for example, a bulb here. Or if you put a marker, of course, it's a passive source. It reflects light, which is produced by the light. Right? So, and of course, after reflection, it sends rays in all possible directions. So now we just need to pick this ray, and that ray out of all this infinite number of rays. Okay, so of course, out of this infinite number of rays, one, of course, will go parallel to the optical axis, which is the ray number 1. Okay, it goes parallel to the optical axis, and after the lens, it goes to the far focal point. Okay, ray number one. But of course, using one ray is not enough to find where the image is going to be. So now you need to use any of those. So I will still use them all. So the second ray, it's a reversing situation. If you pick the ray, a ray, which goes through the near focal point, after the lens, it must go parallel to the optical axis. Okay. And after the lens, it should go there. Is it parallel? Okay, good enough. But this is not long enough. So now let me extend it. So now you can see immediately where the image is going to be. But you still have a ray number 3, and if you want, you can draw even ray number 3. So it will, okay, let me label them. This is 1, this is 2, and now ray number 3. Okay, I slightly displace them, but again, it's a graphical. So this is the ray number 3. Nothing fancy, especially for converging lens. It's trivial, but I remember lately I couldn't get to this material in the lecture, so but when I used to, I was faster. And on the exams, when I used to give a problem like this, lots of troubles. There were lots of math with these rays in all possible directions. Like it was not great. So I was quite impressed because I remember myself, and we didn't have any troubles with these rays. Just one this way, second. It's a quite banal situation, but still, it still was a mystery for me why students couldn't reproduce this. Okay, so the image is going to be over here. So this is image. And of course, we can characterize it. Is it upright or inverted? Inverted, because it's upside down. This image, I mean, the object is up, but the image upside down, so it's inverted. So it's inverted. And is it virtual or real? If you position over there the screen, and I ask lab TAs to demonstrate that during the lecture, right? So if you position over there a screen and illuminate it properly so that enough light would be sent, so you can see it on the screen. So it's a real image. And also another test, because all these rays, the image is produced by converging rays. Converging. So it's a test. It immediately indicates that the image is real. So real and inverted. Okay, so I'm planning to give a problem, so something either object outside of the focal point or inside of the focal point. Now let's look at the inside of the focal point situation, right? And that should be enough. We just had a big debates with other instructors. Should we include this material in the exam or not, right? So that's why we decided, okay, so among the multiple choice questions. So now let me put a new bullet. Okay, so any questions about this? Again, it was in the past, like about 3 months ago, just very quickly look through those problems, right? And again, I'm planning to ask only for the ray tracing, no formulas. So now an object, what is the object inside of the focal point, inside of a focal length? Okay, again, I will start with the optical axis. Okay, straight enough. Then, let's say this is my converging lens. Okay, good. And again, my 3 points. Let's say this is the F near focal point, the center, and somewhere over here, there will be far focal point. And now I'm going to position, of course, object within the focal length. This is the focal length. So here was outside and now inside. And on purpose, I drew the focal length longer because most of the stuff is going to happen over there. Okay, so now I use blue. So let's say this is my, okay, straight enough. So this is object. Right. So I want to find image of this object. Again, using ray tracing. And this is slightly more complicated. Okay, let's start with the array number 1. I just followed the order. Good? Great. So ray number one, parallel. Again, this object, the tip, creates rays moving in all possible directions. We just need to filter out those which we need. So parallel to the optical axis, there it is. And according to our analysis, it should go through the far focal point, so through this. Well, it's a long distance. Let me, oops. Okay, good. So ray number one. So that's, okay, let me draw it here. I mean, right, it's ray number one. Okay, with ray number two, it's slightly more complicated. Because what if we just follow this rule? So if a ray goes through the focal point, then it will be deflected parallel to the optical axis. But in our case, if we send the ray through the focal point, where does this ray go? In the opposite direction from the lens. So it's not going to contribute anything to the image formation. You see? Yeah, if you keep track of the ray which is created over here and goes this way, it just flies away from our. So, but let me ask you this question. What if I pick this ray? Okay, let me use green. This ray, which, imagine this ray which goes along this line. Imagine, of course there is nothing, but what if you imagine the ray which goes through this focal point and passing that tip of the object? You see, what will happen to this ray? Of course, it will be sent parallel, right? But what if I pick out of this ray which goes along the same line? The lens doesn't care where it was originated. It just sees, okay, it flies along this direction. I know what to do. After me, I should send this ray parallel to the optical axis. So essentially, you just need to create this line, and create a ray which goes along that line. Usually, I draw this dashed line in order to get the direction, and then pick a ray which follows along that direction. And after the lens will send it parallel to the optical axis. This is the only subtle point for the case when the object is within the focal distance. So this is ray number two for the case when the object is within the focal length. Okay, even now is already enough in order to see where the where the image is going to be. But I'm still going to draw ray number three, which is trivial, which goes through the center of the lens. Okay, so now you see it looks like all our rays are what are they doing? Diverging, spreading, diverging. So of course, you cannot create a real image. They're not creating a real image. So in order to see the image, what do we have to do? I should have taken the lens for the exam review session. We need to put our eye over here. What if you take your eye and look through the lens? This is your eye. Okay, my eye. And look through the lens. What are you going to see? Now it's a collaboration between your eye and your brain. What happens? So your eye sees that this ray comes from somewhere along this line. Then your brain also sees this ray, and again, in collaboration with your brain, start thinking, aha, this ray comes from some source which is somewhere along this line. And this ray comes from some source which is along this line. So let's extend those lines and see where our brain is going to see the virtual image. There is no real image. It's just our brain plays tricks on us. So we're going to see this. So let me use maybe blue. Yeah, let me use blue color. So our brain will see that it looks like that ray comes from the source, which is somewhere along this line. Then this comes from the source, which is somewhere along this line. And this ray comes from the source, which is somewhere along this line. And of course, all these three extended lines must intersect at a certain point. And that's essentially the point where your brain is going to see, although there's nothing over there. It's a virtual image, which is created in our brain, by our brain using those rays. Because you see, rays are spreading, diverging. It's impossible to have a real image. So we're getting virtual image. And essentially, this is the magnifying glass. We usually position it closer to the object, and we're seeing virtual, bigger, larger image. So this is, you know what? I should have probably used a different color. So this is our image. And immediately we can characterize it. I already said it's virtual because if you position over here the screen, physical screen, you're not going to see anything over there. You need to look through the lens in order to see that image. So it's virtual, your pure imagination, essentially. So image, virtual. Or another, why you come to the conclusion it's virtual, because it's created by the rays which are diverging. Here, all these rays were converging in order to get the image real. If rays are spreading, diverging, it's a virtual image. Okay, and upright or inverted, obviously it's upright. So because they're in the same direction as the object, so it's upright. So image, virtual, and upright. So two situations, nothing else can be. So object within the focal distance and outside of the focal distance. And again, all the analysis is reasonably simple except for the ray number 2. And again, I think for your level, it's not something complicated, right? You should be able easily to draw this. But I remember when I was working with one of my students in the lab, and when we had to very quickly draw these rays, I was surprised that he had some troubles doing that. Okay, guys, good. Again, diverging lenses are slightly more complicated. Again, not significantly complicated, but anyway, so I decided to focus on the converging lenses. Okay, so I will scan this, of course, send it. All right. So diverging. Okay, enough. So let me erase this. Good. Because I want to stay in this part of the whiteboard only. So now let's play with this formula, because as I said, most of the problems about finding magnetic field is about that particular. Okay, it should be enough for now. So two parallel wires, infinitely long wires, horizontal, like this. One is, okay, let me use blue color. You know what, let me say it's a problem number 3. No, problem number 2. That was number 1. So now let's say this is my first wire. Cross, it means into the board. So that's, let's say, I1, and that is the 5 amp current. Then let me draw this line, horizontal line. And the second wire with the current, let's say here somewhere. So, and it's I2, 2 amps. A dot, it means towards us. 2 infinitely long straight wires. Let me write. So we have 2 infinitely long straight. Oh, yeah, it's correct. Straight wires. Distance between them is given. Let's say this distance is d. I think no numbers are given. Okay. So distance between them is 6 centimeters. Yeah, currents are given, distance is given. Okay. So we need to find a point along this line at which the net magnetic field will be 0. So in terms of physics, this current creates its own magnetic field, which extends all the way to infinity. This creates its own magnetic field, which extends all the way to infinity. So we just need to discuss superposition in this region, and that region for if it's possible to have a 0 net magnetic field or not. And then we will introduce some variable and actually calculate the exact position of that 0 point. Okay, so now let me write it down. So we need to find which way I wrote it. Wait, I wrote too much. Let me write a point along, okay, this line, the line where B net equals to 0. Net magnetic field equals to 0. Okay, this is the line. So pretty much I see you already started twisting your arms. Yeah, so we need to find first a contribution to the net magnetic field from the blue wire, from the green wire, and see where cancellations are possible. Right, so you remember magnetic field lines form circles centered on the wire. So over here, I will draw a couple of them. So let's say this will be, okay, the first direction, right-hand rule number 2, outstretch your thumb in the direction of the current and curl your fingers around the wire. So it will be this way. Okay. In the green, something similar. Let me draw it over here. Okay, slightly distorted. Okay, so it will be this way, magnetic field. And now, of course, I can draw a magnetic field at this point created by the blue wire will be, of course, straight down, because you remember magnetic field vector is tangent to the magnetic field lines. That's how we introduce those lines. So this will be our B1, and over here, for example, it will be our B1 at that point. And B2 over here again should be tangent. And over here, again, it will be tangent B2. Okay, so now we have everything that we need on the picture, and now we can start analyzing. You know what, let me draw this dash line and this dash line. Okay, so this region, from that infinity to the first wire, is it possible to have a 0 net magnetic field in this region? Okay, yeah. Okay, so let's start thinking. So magnetic field B1 is up, magnetic field B2 will be down. So directions are opposite, great. There is a chance that there will be cancellation. It's a first step. Second step, we actually need to see, we need to look at the magnitudes. Because sometimes if vectors are in the opposite direction, maybe one is larger all the time, and then cancellation wouldn't be possible. So let's start looking. Maybe over here I can draw that B1 also, right? So let's say this is my, no, B2. So which one is larger? Let's say we pick a 1 point. B1, I1 current is closer to this point, and the value of the current is larger. This is current is smaller and it's farther away. So it means that magnetic field B1 is going to be larger than B2 all the time. So yeah, they're in the opposite directions, but B1 is larger than B2 all the time. So it means that 0 point is impossible. It doesn't matter if you go all the way to infinity. Of course, if you go all the way to infinity, both of the fields will be essentially 0, but it's not the point which we want to discuss. So anyway, let me write something. B net is not equals to 0 since B1, yeah, larger all the time than B2 everywhere. Right. Okay, so that's region can be excluded. Now, this region between the wires, possible? Of course not possible, because both of the magnetic fields are in the same direction. So cancellation is not possible theoretically. So that is also B net is not 0, since B1 is parallel to B2, no cancellation. Okay, so now it's only last region left on the right side. Okay, and so what's the story? Magnetic field B1 down, B2 up. B2 is closer to the point, and and the value of the current is smaller, so it feels like, yeah, balance. It's possible to find somewhere at certain point balance. So this current is closer to the point, but the value of the current is smaller, right? And the stronger current is farther away, so the magnetic field, yeah, it's possible to balance magnetic fields and find the point where they equal in magnitude but opposite in the direction. So it means, yeah, it's possible. So now we need to find the exact position of that point. So let's pick a completely arbitrary point, which way? Over here somewhere, let's see. And the distance to that point, let's call it x. It's our unknown. Let's introduce unknown, essentially a variable. Right? Okay. And at this point, there should be, of course, B1 will be down, B2 will be up, and at this point, we claim they should cancel each other. Okay, so now let me call it region number 3. So B net equals 0 is possible. So now let's discuss that. So at this point, at the distance x, so we need to write that B1 equals to B2. That's the condition point which we want to find. So let's just use it. Formula is given, mu naught I over 2 pi r. So it's a mu naught current I1 divided by 2 pi. Which distance? X. Amanda, which distance? So this is B1. That's what I'm trying to. So B1, it's at this point, right? And B1, it's R1, it's a distance from the current I1 to the point in question. Yeah, D plus X. D plus X. So we just need to look carefully at the picture, right, to see which distance is actually must be involved. It's a D plus X. D plus X. So it's a B1, and now we need to write B2. Again, it will be mu naught I2 and divided by 2 pi. And now which distance? It's a distance from the source, from the current to the point where, yeah, just X. In this case, it's just X. Yeah. Just everything comes from the picture. Okay, what? Mu naught can be canceled, 2 pi can be canceled, right? And as a result, we will have, so what? I1 divided by D plus X equals to I2 divided by X. So one equation, one unknown, which can be easily solved for X. Of course, now we can use proportion, I1 times that, I2 times this. So I1 times X equals to I2 D plus X. Okay, so all x's must be moved to one side. So we will get I1 minus I2 x equals to I2 times D. Watch my algebra, make sure that I don't make some silly mistakes. It's possible. Right. So now x, of course, equals to I2. But whenever I see minus downstairs, of course, it makes me feel very uncomfortable. But in this case, it's true. It's minus. So I2 divided by the difference between the values of these currents. Okay, so let's plug numbers because they're given. I2 is what? 2 amps, then divided by 5 minus 2 amps and times 6 centimeters. I'm not converting to meters because, okay, the answer will be just in centimeters. You have currents versus currents. There will be, units will be canceled. So just the answer will be in meters. In this case, it's not a crime. So it will be 2 over 3. 3 and 6 can be canceled partially. So we'll have 2. 2 times 2, 4. I'm getting 4 centimeters. Getting 4 centimeters, see? Yeah. Make sense? Okay, so what if I create imaginary this situation? What if I take, so right now we have these two wires parallel like this. But what if I take, for example, this wire and turn it by 90 degrees? You remember we discussed that problem in the class. We analyzed the net magnetic field at the midpoint between these two wires. So you remember what was the situation with the magnetic fields? Magnetic field created by this wire would be somewhat either towards me or away from me, so magnetic field. But magnetic field created by this would be up or down. So what's the angle between those two magnetic fields? 90 degrees. So yeah, you remember that we discussed that in the class. Okay. So in this case, of course, if you need to find the net magnetic field, of course, you need to play simple tricks. Actually, not a trick, so it's a banal situation. But very often when students refuse to draw pictures, as a result, very often they don't see the geometry. And of course, as a result, in order to find the net magnetic field, for example, they start applying something which is just wrong. So that's why I keep... Of course, magnetic fields are vectors. Magnetic fields, we're discussing magnetic fields. Those are vectors. And that's why we can get cancellation, because they're vector quantities, right? Currents are not vectors. Currents, it's just a strange quantity which has directions, which has magnitude, but it doesn't follow rules of vector algebra. Dark, no, it's just I never thought about that, why it's kind of behaves in such a strange way, current. But again, it has a magnitude and direction, but it's not a vector. But magnetic field, it is a vector. And of course, when they're perpendicular, of course, you need to treat them properly if you want to find the net magnetic field. Yeah.
So I'm confused about when the wires are 90 degrees. So that I see their magnetic fields, their lines would end up being 90 degrees from each
Okay,
other.
so let's say this is the current up. Okay, whatever, current 1, and this is the second. And now let's just draw the circles. Current produced by this. It's this circle, right? And let's say magnetic field can be, for example, either, let's say up. Right. So magnetic field up. Now current that way. So again, circle. And what will be the direction of the direction of the magnetic field? Yeah, it's either towards you or away from you. Let's say towards you. So this magnetic field is up. This magnetic field towards you. As a result, you're getting.
So the net magnetic field would be.
Yeah. We're talking about the net magnetic field. Yeah, of course. And that's the problem which we discussed in one of the classes.
Okay.
Right? So, yeah. Again, my point is just try to draw pictures. They help a lot, right? I'm struggling also with upper undergraduate level students when sometimes they refuse to draw pictures, and then of course lots of mistakes, right? Unnecessary mistakes. Okay, so I think it should be enough. And again, usually not much of a troubles with that formula. It's one of the easiest. Enough. Again, as I said, Biot-Savart law, I usually don't give problems about that. Ampere's law. Now, let's just solve conceptual question about Ampere's law. Because it's a little bit tedious, Ampere's law, and mainly like a calculus. So, yeah. So what if we have, let me put number 3. And what if we have this situation? So let's imagine that we have 4 currents. I1, Okay, let me draw it here. I1, then I2, then I3, and I4. And let's assume they're all of the same value. 1, 2, 3, 4 equals to 2 amps. Just to review ideas, rules. So the magnitudes are not that important. Okay, and of course, each of these currents are going to produce the magnetic field. So let's say we're interested in the net magnetic field, right? So something like that. And we want to apply Ampere's law. So first of all, before we start applying Ampere's law, what do we have to? What should be our first step in applying Ampere's law? Yeah, you can pick a coordinate system, but it's not that very important. Yeah, you need to pick an Amperian loop. You remember when we apply Gauss's law? First of all, we try to find Gaussian surface. If you want to apply Ampere's law, you need to pick an Amperian loop, right? Okay, so let's assume that somebody pick an Amperian loop of this shape. No, let me use blue. This shape. And again, it can be any loop as long as it is closed. Right. Actually, the loop is closed by the definition. So any loop, closed curve. And again, once you pick the loop, next step you have to pick what? Ali? You remember, of course, integration over a line. Of course, now you remember. Of course, you need to pick the direction of the loop, right? So once you start applying, it starts coming back, right? So let's assume that somebody picked this direction. Right. So that's our Amperian loop. And okay, so let me just rewrite Ampere's law. It's a B dot dl equals to mu naught times I enclosed. So essentially, what we need to find the value of this integral. Let's find the value of this integral. Or sometimes the question can be slightly twisted. Let's say the value of the integral is given and you need to find the value of one of the unknown currents. You remember we solved something like this in our classes. I usually use it as a clicker question in the class. Okay. Do we need to do integration? No, nothing fancy, right? So we just need to pick correct currents and with the correct signs. Banal. So it's a mu naught. And so which current is the positive current? You remember the right-hand rule number 2, essentially, right? So you need to, once you pick the direction of integration, you need to curl your fingers in that direction, and your outstretched thumb gives you direction for the positive current. You remember that. The point is just to refresh this rule, right-hand rule, the only point of this question. Right? Otherwise, it's quite banal. Again, it's all reviewing. We're not introducing something new or something fancy, right? So curl your fingers in this direction, and your outstretched thumb is into the board. So it means that I2 is positive, and the rest of the currents are negative, right? So for the Amperian loop, Oh, how should I draw it? No, drawing hand is too much for me. Okay. In my notes, I made some attempt to draw. It's very ugly. It's scary. So anyway, so this should be positive. Okay, let me write right-hand rule number 2. Right. So I2 is positive. Even let me write plus in front to emphasize on that. Then I1 is negative, and I3 is also negative. Okay. So now we just need to calculate. And of course, you can easily leave your answer in terms of mu naught. It's not a mistake to leave your answer in terms of some universal constant or in terms of pi, right? So if an instructor really picky, start doing something, but it wouldn't be fair. So all the currents are the same. So this and that will cancel each other, for example. So it will be essentially negative 2. It will be negative 2 mu naught. Okay, so again, it's a banal question. Again, the goal was to review the right-hand rule because, like, Ali forgot it. So again, you're not the first one, and that's why I was start asking. Okay, so how to apply Ampere's law? Yeah, I don't want to do it because it's mainly like almost mathematics. So enough of this. Now let's play with the magnetic forces. There will be like two conceptual questions and a couple of problems. Good? Yeah, awesome. I think I will probably start. I will erase and start from this side. Can I start erasing this? These markers are so good. Sometimes it's difficult to erase them. In every exam session, I keep complaining that after this session, I feel like my shoulder, my arm hurts, right? So I need some kind of physical therapy, professional damage. Seriously, right? I need to bring that idea to the union. Because sometimes it's very difficult to erase. Okay, something similar was discussed in the class, but again, it's a review. So let's say it's a number 4. Right. Conceptual. So let's assume that we have this wire, let's say infinitely long, with current. Let's say current flows this way, I. No value of the current, conceptual question. And we're going to drop a bunch of charges, some of them positive, some of them negative, right? And we're going to discuss or analyze the magnetic force acting on them. So let me start with the first one. Let's say this is my, let's say positive charge, Q. And I want to discuss magnetic force acting on this charge. So first of all, I need to write the force. It's also given over there, but still it's better to have it right in front of your eyes. So first of all, we need to see the direction of the magnetic field. Right? QEB, VB. Magnetic field must be seen explicitly in front of us, right? So direction of the magnetic field lines, circles centered on the wire, and then right-hand rule. So let me draw a couple of magnetic field lines. Direction should be here towards us, here away from us. So these are magnetic field lines. So it means that magnetic field above towards us dot. Every time I'm imagining that arrow flying away towards. So these are magnetic field. And below, of course, it will be away from us. So that's B. Great. So right now, what can you say about the force acting on that charge? You're looking right. What? Okay, speak up. Yes, of course. That was my point. That's why I started walking around the table. What is missing? Velocity. Of course, we need to introduce velocity. Again, as I keep telling you, in the magnetic world, it's a world of dynamics. Everything must move in order to see some effect. In order to produce magnetic field, charge must fly. In order for a charge to experience magnetic force, it must fly. Everything must move in order to see any magnetic phenomena. So it's all world of dynamics. So let me give you some force or velocity. Let's say it's to the right, my right, your left. So let's say this is the velocity. Okay, so now, of course, it's a legitimate question to what's the direction of the force. And so what are you getting? What's the direction of the force? Conceptual. Yeah. 3 fingers. Or it looks like you're a 3-finger guy. Down? I have no idea. I need to apply it, right? So down, down. Because So first of all, it must be perpendicular to both vectors. Magnetic field dot is towards us. And velocity that way. So the force must be either up or down. But either which one is correct, you just need to apply right-hand rule. But I like that you're already getting the direction, the vertical direction, right? Yeah. Sometimes it's kind of not funny, but if you don't know what students do to see students on the final exam, because they'll be sitting, right, so doing some funky moves, kind of. Okay, so you told me what? What did you get? Yeah. Because I think you said something down. Okay, down. Let me do it. So V is that way, B is towards you, so I need to position my hand like this. V, the first vector in the cross product. Then I need to position, orient it like this, so now I can bend my fingers in the direction of B, towards you. So thumb is down. Or 3 fingers. This is for the first vector, for V. This is for B, second vector, and this is for C. So V that way, B towards you, so I need to position my hand like this. So V, B, C, right? And with that, I also got, down. So both 3 fingers or curling your fingers, the same, right? Guys, if you're not comfortable with the right-hand rule, you're going to be in a big troubles on the final exam. I kept telling that in my exam review, or in my section, right? But again, at least in my section, there was no any serious troubles. One student had, but he came to my office, and after like 10 minutes, he went out feeling comfortable. So force is down. So now, what if we now have this charge? Minus, negative charge. And of course, as usual, we need to show the direction of the force. Let's say, direction of the velocity. Not, yeah. Again, it's up to you how to handle that. But in my sections, actually, that's why I picked this charge in order to refresh that, right? So, again, you can use left hand or do something. Well, again, it's up to you, right? As long as you get the idea, you can do it however you feel like. But I usually, so what are you getting? Left, right, left. Your left, right? Okay. V is up, then B towards you. So V cross B. I'm getting my right, your. Of course. No. What I did, it's correct. But what I'm getting, so I'm getting this. So V cross B. It's a V cross B. Right? It's a V cross B. But the force will be must be flipped because it's a negative charge. Again, that's what I usually do. First, I find the direction of V cross B and then just adjust it. Or you can use left hand if you feel like, again, but you need to, or do B cross V. So it's again, it's your personal choice how to handle it, right? So, since the charge is negative, but not quite often, but at least maybe like 15-20% of students, they forget that the charge is negative and forget to make those adjustments. Right? And again, that's the only reason why I'm discussing that, because after teaching for 10 years, I kind of know where students have a tendency to make mistakes. All right. And usually it's kind of reproducible from semester to semester, from year to year, because you're all going through the same system, right? So you all come pretty much with a somewhat similar level on average. So F, and again, let me check one more time. So V cross be that, and of course, yeah, this is correct, right? All right. Okay, so let's just one more case. Let's say this is what negative charge and flying, let's say this way, v. So what's the direction of the finally force? Direction of, are you still drawing? Mhm. You're saying up, right? Again, I need, also agree with the force, right? Is the force up? Yeah. Good, good, good. Okay, recording, good. Okay, so let me see. Did you get up? Yeah, you said up. Mhm. So v that way, b, into the page. No, into the what?
No, I mean like.
You're applying right hand rule. Okay, so v that way, magnetic field is into the board, cross, yeah, into the board. So I need to position my hand like this. V cross b is down, but since the charge is negative, so the force will be up. So it's a v cross b, but since the charge is negative, so the actual force will be up. Yeah. Okay, I think it should be enough, right? So to review it. So now let me, actually I should be able to fit it here. Next conceptual question. Again, all these forces in the electromagnetism, they're sensitive to the sign of the charge. So, and sometimes students forget about that. So if charge is positive, under the same conditions, force will be in one direction, but if the charge is negative, force will be in the opposite direction. So we need to keep that in mind all the time. So what if we have this magnetic field, uniform magnetic field, represented by these crosses? So that's B. And let's shoot two particles, charged particles. The first one is down. Let me use blue. No, the first one is, the first one is from the top. So let's say this is Q1, which flies this way. That's velocity. And immediately, what will be a trajectory of this particle? No, just in the words. Is it a straight line? Is it following letter Z? Or so what's the trajectory, the words? It will not be a straight line. Okay, it's a good start. Any fancy names? It's a lab class. It's a cyclotron motion. It's a cyclotron circular motion. If we assume that there are no any energy losses, it will be just a pure circle. If there are some losses, of course, it will be somewhat spiraling in a trajectory. So it will be, what's the direction? I think it's a positive charge. No. So it's not a positive. We actually need to answer the question. What's the sign of the charge, right? So trajectory is given. So we know it should be a circular motion. And in this case, let's say it's this. So this is the cyclotron motion, trajectory of this particle. Circle with whatever radius. Okay, then at the same time, there's a second particle entering this field from this point. So Q2 flying with this. And of course, it will again experience circular motion. And let's say it's travels like that. Okay, so by looking at this picture, we need to answer the question, which particle is positively charged and which particle is negatively charged? Very typical question for the final exam, and we discussed that. You discussed it in the lab class, and I did it when I substituted one lab TA. So yeah. Of course, you already started doing that, right? So yeah. So ideology of this problem. So we just need to look at that formula. F equals QVB. An idea is Can you see the direction of the magnetic force by looking at the picture? Of course, it's obviously, right? So it must be towards the center of the circle because that force creates this circular motion, provides this centripetal acceleration, which is the inevitable acceleration for any circular motion. So by looking at this picture, of course, you can say force acting on the first charge at any point. Of course, I usually pick the beginning, right? You can pick any point, for example, this or that. The analysis will be the same. So this will be the force towards the center. Every time by looking at, understand? By looking at the curve, you should be able to tell immediately what's the direction of the force. Now, so a direction of V cross B. A magnetic field, as an experimentalist, you provide it. You know the direction of the magnetic field. Direction of the velocity, every time, physics 1, it must be tangent to the trajectory. Every time. It's an instantaneous velocity, right? So velocity there, magnetic field cross away from us. So it's a V cross B, right? V cross B. So V cross B is that way. Okay, so let me draw it. This is V cross B. So since direction of the force and V cross B the same, it can be only true when the charge is positive, because this is universal formula. So far, no one has found any examples where it failed to work. So it all works all the time. So if directions are the same, it can be only when the charge is positive. Right. So let me write. If F is in the same direction as V cross B, then Q is, okay, let me write just Q is a positive. So in our case, Q1 is positive. So in our case, Q1 is positive. So this is, okay, let me write underneath, Q1 is positive. Okay, now let's do the same with Q2. Force towards the center of the circle. No options. F2. And V cross B. V that way. B into the screen. So V cross B down. V cross B is down. So I'm running out of colors. Let me use blue over here. So it's a V cross B. So directions are opposite. So it can be true only if this particle negatively charged. So analysis is quite straightforward, nothing fancy. So if F is anti-parallel to V cross B, then of course Q is a negative. Particle is negatively charged. In our case, Q2 is negative. So once you know the idea, it becomes quite straightforward, trivial. Right? And again, quite often I give questions of this type. Okay, so now let's solve problem. Okay, any questions about this? No, it should be like this. And that's what quite often people from the world of elementary particles do when they analyze photographs from cloud chambers or bubble chambers, if those chambers are still being used. So now let's solve problem about this cyclotron motion. So let me call it a number 5 problem. Let me separate it better. So number. Okay, so this is some new problem. So let's assume this situation. Let me draw. It will be easier to explain. Okay, so let's assume that over here there is a hole. And on this side, we have essentially some accelerator. Maybe just a simple parallel plate capacitor, or maybe some Betatron or cyclotron, which you discussed in your lab classes, whatever accelerator. Basically, it allows us to get some high energy particles. Let's assume protons. So let's assume at this point we have a proton. So let me just use so let me write it's a proton with kinetic energy k. And it means that, of course, it will have some velocity. Velocity is not given, k is given. So we have let me write a proton. K, kinetic energy, is given. Okay, so now, after this hole opening in the accelerator, at some distance d, there is a wall or barrier. Let me just call it wall, easier to write. And so if we just let the proton fly, of course, it will just hit the wall. But we don't want that. We want, for whatever experimental reason, we want to turn this proton by direction of the proton by 90 degrees. So now it flies this way, but let's say we want to fly it straight down, and we want to barely avoid collision with the wall. So we can use magnetic field. We just over here need to create the area of the magnetic field, and magnetic force using the cyclotron motion will be able to we will be able to turn it. It's sort of like here's the, let's say, cyclotron motion. Let's say at this point a proton enters magnetic field, and if you create the conditions at this point, proton will be perpendicular. Velocity of the proton will be perpendicular to the direction of the original, right? Or you can turn it backward, but of course you need to have some space. Yeah. Now we need to find that intensity so that it would turn by 90 degrees and barely pass the wall. Yeah. Why not? Again, yes, actually, that's what I think we have accelerator. Van de Graaff accelerator. You know this tower in Pinansky building? In front, there's a great tower. Essentially, it's a Van de Graaff generator where they accelerate particles to a huge speed, and then they keep turning them along the path, guiding them to some experiment. And I think most likely they use something like this. I wouldn't be surprised. I never worked over there, right? So I went there a couple of times on a tour. I kind of didn't pay attention to those details. But yeah, it can be used. Right? Okay. So essentially, we're going to create what's the direction of the magnetic field with the dots. Okay, so over here, dot, dot, dot. So that's our magnetic field B, uniform magnetic field. And over a region, which is essentially a square. So this width is D, and this length is also D. So essentially, it's a square D by D. Maybe even I can create this. So this is called, what's it called? Bending magnet. Bending magnet. Essentially, it's a bending magnet. Maybe let me show it. Okay, so now particle enters this way. Of course, it will, yeah. Dots. At least that's in my notes, and I analyzed. It looks like I should be able to get the right. And you see, it enters the magnetic field just at the very top, and from the left side. Okay, so of course there will be circular motion. Let me check, since you asked me. Dot it towards us, so it should be like this. So magnetic force will be down, and it's a proton. It's a positively charged particle. So of course the trajectory is going to be like this. And we want to barely pass the wall. So pretty much it's right next to the wall. Magnetic force at this point should be down. the velocity will not be zero. We assume it's just changing the direction because we assume it's a vacuum, right? So there are no any energy losses, right? And magnetic force cannot change the magnitude. Essentially, it's a uniform circular motion, cyclotron motion, right? Okay, so yeah, maybe I should. You see, it's a cyclotron motion. So first, I will just find first the magnitude of the velocity, right? And then the real physics, and then the real physics. So a v of the proton. First, let's find v of the proton. So it will be, okay, it's banal physics, of course, 1/2 mv squared. It's a kinetic. Kinetic energy is given. So I just want to get the velocity. So of course, the banal stuff. So from here, I can get the velocity will be equal square root of 2k over m. Okay, so great. So that's preliminary step. And now physics, actual, which is interesting. So, of course, you need to use what? Formula for the cyclotron radius. I never give that formula in the formula sheet. So every time I expect from students to, come on, it's a quite simple derivation, half a line derivation, if you can call it derivation. So force, magnetic force. Let me show, for example, over here. So that's the magnetic force, right? We just play with that. So now let me discuss that cyclotron motion. So magnetic force, Q, V, cross B. Direction, we see it every time towards the center. Essentially, we need to know the magnitude, right? Okay, let's find the magnitude. Fm, Q, V, B, and sine. What? Oh, I wanted to ask, sorry. So what's the angle between V and B? Picture, you see? For example, you take this point. 90 degrees, of course, 90 degrees. Sine of 90 degrees is 1. Sine of 90 degrees, it's 1. So essentially, value of the force, QVB. And it's all the time in the radial direction. Okay, so now we just need to apply Newton's second law in the radial direction, and that's what you did in your lab lecture, right? So Newton's second law in the R direction. So essentially, it's a, maybe I should move to this side more often because I'm blocking that side. So Fr equals to mass times acceleration in the radial direction. So do you remember acceleration in the radial direction? Centripetal acceleration, of course. It's a v squared over r, centripetal acceleration. And the force, we just wrote. So, so this comes over here, and acceleration is centripetal. So you'll get QVB equals mass v squared over r. So now we just need to cancel v, 1v on both sides. So here v and here 2v. So of course one can be canceled. And here we will get r cyclotron equals to mv over qb. So essentially the formula for the cyclotron motion, but I never given this formula in the formula sheet. Pretty much every time I expect from students, write the magnetic force, formula is given. This acceleration, centripetal acceleration is also given. So just write this, cancel 1v, solve it for r. It's not a rocket science. It's okay, so that's what we need. And so now we want to get the value of b so that a particle will barely pass the wall and also at the same time having velocity straight down. So what should be the value of our cyclotron? D, of course, just D. So it should come to this point which is D. Okay, so that's it. So R cyclotron, which is mv over qb, must be equal to d to barely pass the wall. And we need to find the magnetic field, right? So we discussed it, but I didn't write. So we need to find B, the value of B, to turn velocity by 90 degrees and to barely pass the wall. So that's our unknown. So we can get that B equals to mv over q times d. Velocity we found through the kinetic energy, right? So it will be m over q times d and square root of 2k over m, right? Square root of m can be canceled, and it will appear upstairs, right? Square root of m. So this m and that m, so you will get 2mk over, 2 deep, just upstairs, and divided by q times d. So that's the value of the magnetic field that you need to provide in order to turn the particle by 90 degrees and barely pass the wall. Okay, sort of something different, something new. Essentially, again, every time QVB equals mv squared over r. And again, I expect that to be done. So last night I was preparing something new. So, for the exam review session. But again, about cyclotron motion, you cannot create something complicated, right? It's possible, but come on, you still needs to be. You should be able to solve it within like 20 minutes or something. And again, based on my experience, if students know pretty much material solidly, so that students should be able to live within half of the given time. Okay. Any questions about this? So now another problem, but now about the magnetic force on the wire with the current. And a few years ago, I gave a problem like this on the exam, and there were lots of troubles. So that's why it ended up on the exam review session, because I see where the problems are, and I'm trying to punch at that point. Yeah.
If you wanted to turn it more or less, would you just shrink or grow the area?
In this case, if you want to turn it more, of course, you will increase the area of the magnetic field. So it will, if you increase it to this level, it will be and fly that way. So if you increase it to the distance, if this height is 2d, so it will be able to complete half a circle and turn the direction to the opposite one. Sometimes that's what can be used in order to turn the particle back, right? So.
No, like, no, that answers the question, but would the magnitude stay the same even if it stayed that?
Okay, if you change the magnetic field, of course, yes, then the radius become smaller. If you increase B, radius larger. Then of course you will start hitting the wall, right? So it will be just collide with the wall. But if you start reducing it, of course, there will be opposite effect. Okay, so now let's solve the problem which created where students had troubles. This whiteboard becomes dirtier and dirtier. So L-shaped wire. So one part is horizontal, one part is vertical. The same current flows, and everything is exposed to some uniform magnetic field. So let me draw the picture. So that will be number 6. All right, so let's say we have L-shaped wire. If you feel like you can play with the window, you can open it, close it. Okay, I'll probably draw the picture first. So let's say this is the first piece of wire, and then the second. Current, of course, the same. So let's say this is I, and of course here will be also I. Then length, this is, let's say, L1, and this part is L2. And it needs to be exposed to the magnetic field. Let's assume it's uniform. So cross, 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 cross. Okay, enough. Pretty much the whole wire is exposed to the magnetic field. I don't want to draw another line of crosses. All right. Okay, so the question is we need to find the net force acting on this L-shaped wire. So we need to find F net magnitude. Magnitude of the net magnetic force acting on this wire. So in terms of physics, we are at the very fundamental level, right? So there is a current exposed to the magnetic field. So plus the wires are straight, two pieces of straight wires. So we just need to grab this formula and apply it correctly. So pretty much not much of a physics, just mathematics to some extent. So let me write F equals to I L cross B. Do you remember what determines direction of the vector L? Yeah, direction of the current. There's only one direction in the wire, and that's kind of obvious, more or less. But still, trying to refresh. Okay, so as a result, now let's find, and yeah, you need to split problem into two, and that's what students refuse to do in on the exam, right? So there was lots of strange things. So let's find the force acting on the first section of the wire. So what's the direction of the first section on the first acting on the first section? All right. In this case, just L cross B. Right. Direction of L, direction of the current. And then cross it with B. B is into the board. So L cross B. So the force is up. Or three fingers. This is L. It's correct. So L, B into the board. So the force is up. Yeah. So this will be the force F1. Okay. So F1 is up. Okay, let me write upward. Again, right-hand rule. Number 1. And F2, the same thing. So L is down. B is in, so L cross B, it will be to my left, your right. Yeah. So this will be F2. F2. So F2 is to the right. Okay, so now we have what situation? Two perpendicular forces, like that situation when we try to discuss magnetic fields. Two perpendicular magnetic fields here, two perpendicular forces. Mathematics, the same. Mathematics is the same. Because mathematics doesn't care about the nature of vectors. Is it a vector? Okay, I will treat it as a vector. But what's your nature? I don't care, right, essentially. So F1 is up, and F2 is to the right. So we have this configuration. So if we want to find the magnitude of the net force, we just first need to add them graphically as vectors, and then do the proper voodoo. So this will be F net. And now, of course, we need to use Pythagorean theorem, banal Pythagorean theorem, right? Okay. So F net equals to square root of F1 squared plus F2 squared. I should have written also the magnitudes of those forces. Maybe underneath I will write. So F1, it's a I, L1, B the same, and sine. What's the angle between L and B? 90 degrees. They all L horizontal, B also horizontal, but into the board. So of course 90 degrees. Sine of 90 degrees. Sine of 90 degrees is 1, so it will be I L1B. And of course, in a similar way, F2 will be I, the same current, but L2 times B. Right? So F2 equals to I L2 times B. So now we just need to plug that and calculate. Okay, simplify, not calculate, nothing to calculate because numbers are not given. So square root of I L1B squared plus I L2B squared. So now we just need to simplify. I and B can be factored out, and inside there will be square root of L squared plus L squared. IB and square root of L1 squared plus L2 squared. Again, the problems when I gave it as an exam, because students just refuse to draw the diagram. Once if they draw a diagram, of course, it's obvious that you need to apply Pythagorean theorem. Okay. Good? No questions? Yeah. So now next is we need to review Faraday's law, then inductors, one problem, of course, on the inductors, electromagnetic wave and interference. So it feels like 4 problems should be. So first, conceptual questions about Faraday's law. Good? Good? Yeah. All right, so let me probably erase this. Let's be consistent and move from left to right. And yeah, it should be enough space. You know what, this eraser is much better, pleasant. So first conceptual, basically try to use Lenz rule. So that will be number 7 and Lenz rule. So let's imagine this situation. Okay, so there is a conducting loop, and let's say we somehow manage to shrink it. Maybe it's adjustable, some conducting polymers or whatever. So let's say this is the original shape. Let's call it let's call it R1. I think that's what I did. So this is R1, and then we shrink it, and then will be R2. Right. So conducting loop. And of course, it must be exposed to some external magnetic field. Otherwise, nothing will be, nothing will happen. So let's assume it's cross into the board. So this is external magnetic field. So B external. And so conducting loop, Diameter changes conducting loops. Ой. Loops. Diameter changes. So from R2, I said diameter, okay, radius. Radius changes. So from R1 to R2, and of course, R1 is larger than R2. So we need to see, we're going to get any induced current, and if yes, then what's the direction of the induced current? Because conditions kind of met. We have conducting loop exposed to the external magnetic field. Of course, we can introduce magnetic flux, right? And if that flux changes, then of course we should see induced current, right? We just never discussed situations where the area changes in this way, right? Okay. So essentially, we just need to apply this Lenz rule. Okay. Flux. So we need to see what happens to the flux. Inside of the flux, we have three parameters: B, A, theta. And every time I force students discuss them all. Okay. So external magnetic field, area of the loop, and the angle between B and A. Do we do anything with the magnetic field? It's constant. Yeah, we don't do anything, so it's constant. It's constant. Then area. I can pick, for example, area vector in the same direction as the external magnetic field, and the angle will be what? 0 degrees, right? So you see magnetic field is in. Area, you can pick either out or in, it's up to you. It's an open loop, open surface, not closed surface, you have a choice. So anyway, 0 degrees. If you pick area vector out, it will be pi, but anyway, it's constant. So angle will be constant all the time, no matter which direction of the area vector you pick, right? So angle is constant, agree? Yeah, good. So angle is constant. And what happens to the area? Of course, it goes down, right? Because we shrink it. So area goes down. So now, if you multiply them, B, A, cosine of theta, of course, now you can come up with a conclusion. What happens in time with the magnetic flux? Of course, magnetic flux is also going down because area is going down. So magnetic flux is going down. Okay, great. So we come to this point, and now it's immediately we need to recall the story. All right, of the Lenz rule. So the conducting loop doesn't like when flux changes. If flux is constant, the loop is in nirvana. HAPIC absolutely doesn't do anything, just sleeping. But once flux starts changing, if it's increasing, the story is the loop starts rebelling, behaving like Che Guevara, right? So inducing current in the proper direction so that the induced magnetic field is in the direction opposite to the direction of the external magnetic field within the loop, because it tries to suppress the. In this case, it's dying. It's dying. So sorry, it's dying. So it's a second situation. Second situation. So it sees flux is dying, but it wants to keep flux as constant as possible. Oh, let me help you, like Florence Nightingale, right? So start driving the induced current in the correct direction so that the induced magnetic field is in the same direction as the external magnetic field, again, within the loop, because it tries to support dying flux. What is outside of the loop, who cares? It wants to support dying flux. Again, that's the story which I usually create explaining the Lenz rule. Okay, so it means that B induced is in the same direction as B external. We see the direction of external magnetic field, so immediately we can say the direction of the induced magnetic field will be also the same, according to this story, right? So it means that within the loop, I can draw another set of crosses. But now they represent B induced. Great. So now we know the direction of the induced magnetic field. And of course, this induced magnetic field is created by the induced current, direction of which we want to find. We need to apply right-hand rule in order to connect those directions. Induced magnetic field is cross is in. So essentially it's like this towards me. So I need to match this direction with my fingers. If I curl my fingers like this, so grabbing the loop, so I'm getting the direction of the current. If I position like this, it's a wrong direction because magnetic field towards me, but direction of this current will give me that magnetic field, which is wrong. So I need to position it like this. So now I curl my fingers, just grab it, and it gives me direction of the induced current. So every time these 3 steps, okay, from this point, I push in the class. So now I can get that I induced. Oh, and I forgot which direction I pick. So again, it's in. So it's a clockwise. Yeah, it's a clockwise direction. Cross in. Yeah, so it's like this. So it's clockwise direction. CW direction. And let me check if I induce CW. It's just basically I applied that right-hand rule, which we used here. Direction of the magnetic field and direction of the current are connected to the right-hand rule number 2. But now we're applying in the reverse direction. We know the direction of the field, magnetic field, and we want to get the direction of the current. So it's the same rule, but are applied in the reverse direction. I just didn't want to introduce another right-hand rule, which is very often is done in the book. So if you feel comfortable with that, you can go that way. It's just a question of preference. Yeah.
One more time, can you walk through why, like how you?
Okay. So the rule is, so first analyze this, right? Then in order to come to this point, we need to see every time what happens to the magnetic flux. And then I create the story about if something is growing, so of course it behaves like a rebel, like moving against the system, like Che Guevara, blah, blah, blah. So it means that magnetic fields within the loop are in the opposite directions. If it's dying, it's trying to support, so directions are the same in order to make flux live long. Of course, it will die anyway sooner or later still, but it will live a little bit longer. And then once you know direction of the induced field relative to this, because usually this is given, then you can get this current by applying this right-hand rule. Because those the direction of the current and direction of the field are connected. So now our situation, induced field, red crosses. Yeah, red cross. So that way into the board, within the loop, because you remember it supports or it suppresses flux. Flux is within the loop. Every time we need to discuss what is within the loop. So now I need to curl my fingers so that my fingers would match this direction in.
So I guess the confusion of having is if you put the red crosses outside of the other.
That's why I keep telling, outside we don't care. It wants to support or suppress flux. Outside, it's whatever outside.
So that was the question I was asking. You want to
Inside, only inside. Because again, the whole story created was about flux, supporting, suppressing flux, because the almost like universal rule systems doesn't like changes. Changes in what? It's a question. In this case, changes in the flux. In the case of the Newton's first law, particle flies in the same direction with the same speed because it doesn't want to change its state of motion by itself. In order to make some changes, you need to apply some external force. Right? Or me waking up in the morning if I have classes at 8, right? So I have 3, 4 alarms waking me up, right? Because my system wants to sleep, right? So it wants to keep the same state of happiness. Right? So in CW direction, so it means that current will be, okay, this marker should be changed soon. So this will be I induced. Great. Make sense? Or whatever rule you prefer, analysis, right? So I created this, try to add some fun. All right. So now let me quickly discuss another situation using this. I think we solved in our recitation class something like this. What if we have this current and then big problem? So let's say this is the direction of the current. It's constant, right? Of course, magnetic field lines we can easily find. It will be over here towards us, dot crosses. So let's say here we have a dot, here we have a cross, again, dot, cross, cross, dot. So that's B external. In two loops, and very quickly, let's discuss what if I have the first loop over here and push it or drag it that way. You remember we discussed something similar in the class. So let me call it loop number A. You know what? A is our area. No, I don't like this. Let me just call it loop number 1. Loop number 1. So, okay, loop number 1, let me put 1. And again, we need to analyze 3 quantities, B external, area, and the angle. Anything happens to the area? No, we keep it the same, so it's constant. Angle. You can make it 0, you can make it pi, it's up to you, but anyway, it's constant. In time, it doesn't change. What happens to the magnetic field? Okay, at this point, I try to confuse at the very beginning students from my recitation class. No. I can say even, okay, so I usually say this. Look, within the loop, the value of the magnetic field changes. Here it's larger, here it's smaller, larger, smaller, right? But those changes are in what? Even if I don't move it. Those changes are in space. Yeah. And Faraday's law doesn't care what happens in space. Faraday's law, for whatever weird reasons, right? So it only cares about changes in time. Right. So something, magnetic field can change in space over the loop, but if that magnetic field doesn't change in time, then nothing is going to happen. So you need to change it in time. And in our case, if you drag the loop that way, of course, magnetic field at every point is going to get smaller and smaller and smaller. If you pick this point relative to the loop, so let's say now it's a 5 Tesla, you move it together with the loop, now it will be 4 Tesla, 3 Tesla, 2 Tesla, and so on. It keeps decreasing. Magnetic field, Okay, rate, it depends on how fast you're going to move. Are you going to move it linearly or exponentially or whatever time dependence? So it's up to you, right? And it's not going to change the direction of the current. It will change the value of the current if you're going to move it faster, slower, right? So, but direction will be still the same, right? So it's your additional fun. So anyway, so in this case, flux is what? Magnetic field is going down, so flux will be also going down. It's the same situation like the previous one, right? So now the system becomes supportive, like Florence Nightingale, or poor thing, you're dying, right? Let me help you. Right. So B induced will be in the same direction as B external, right? And now let me draw induced magnetic field in the same direction. It means it's going to be represented by bunch of crosses. That's B induced. And you see, every time I draw it within the loop, because that's what's important, within the loop. It's supporting or suppressing within the loop flux. And so now, right-hand rule, in order to get this direction, I need to curl my fingers like this, grabbing the loop. So the direction will be, again, clockwise. Right. Yeah, so this will be direction of the current. I induced clockwise, so I induced clockwise direction. What if I change direction of motion? What if I start dragging closer to the loop, or closer to the wire? Counterclockwise. So if I stand over here and start moving this way, this way, this way, so it will be like an AC generator, right? So I'll be generating current, right? Very expensive current generator. But what if I start moving the loop down or up? Everything will be constant. Even magnetic field will stays the same in time. in time. So of course, in this case, nothing will be produced. So you need to move either away or closer to the source in order to produce non-zero induced current. Okay, good. So it's enough. Now let's solve one big problem. Right. Okay, you know what? Just a second, guys. Before I trip myself. Sort of classic example, U-shaped rail with the moving rod. But to add some fun, I distorted the shape of the rod. It's not just a straight rod, it's at some angle. At some point, it had some kind of circular shape, and here it's sort of a triangular shape rod. It's almost ubiquitous example. You can open any book and you will see that U-shaped rail example. So that was 7, now 8. So let's see. Wait, 8. Right. U-shaped rail. What is given, I will show it on the picture. Right, it's easier. Let me draw the rail. Right. Width is given, L. So L is 0.3 meters. Then rod conducting. Oh, just a second, guys. Let me mute myself. Okay, it was muted. Okay, so rod. Let's say I created this shape rod. Oh, too big, right? No, just for fun. And also for fun, let's say that this angle, for example, alpha, it's not given. And this rod is being dragged this way out, V. And the whole thing, of course, must be exposed to some external magnetic field. Let's say magnetic field is towards you. So this is external magnetic field. Whew. I need to create some kind of stamp to draw magnetic fields. Right? So cross stamp and the dot stamp, so you can, like putting prices in the market. Because it's kind of tedious. Okay, so that's B external, and I think it's also given. Let me check my notes. 0.2 Tesla. B external equals to 0.2 Tesla. I think velocity is also given. Yeah, constant velocity. V is, wait, I just looked and already forgot, 5 meters per second. Right. Okay, I think that's the whole story in terms of numbers. All right. And of course, the rod all the time has an electrical contact with the wire, with the U-shaped rail. So physical and electrical contact. Right? Okay, so the question is, we need to find the value of the induced current and the direction of the induced current. In terms of physics, we are at the very fundamental level of the Faraday's law. We have, you see the loop? You see? Loop. Exposed to the magnetic field. Of course, we can introduce some flux, magnetic flux. And now we need to see if flux changes. Of course, there will be EMF induced and induced current will flow. So it looks like we're at that fundamental level, and so now let's just apply correctly Faraday's law in order to find the value of the current and the direction of this current. Right? Okay, so now let me write what needs to be found. Find I induced, okay, direction and magnitude. Direction plus magnitude. You know, I don't know. It's up to you where to start. You prefer to start with finding the value, then direction. I don't know why I prefer to start with the Lenz rule. I like it. I like applying it. So usually I try to find the direction of the induced current and then the magnitude. So let me put dot and so let's first find direction of I induced. So it's like over here we did. So let's just create another train of thoughts of that type. So again, 3 parameters, the external, area, and the angle. Do we do anything with the magnetic field? No, it's constant. So it's constant. Area. No, let me first discuss the angle. You know what? At this point, I mean, in this problem, we need to pick a direction of the area vector. So let me pick it. Minor compulsion, every time I pick it in the direction of the external magnetic field. I don't like to deal with negative values. So I'm sure that you understand my sentiment. So A. In the direction, again, it's up to you. You can point it up, you can point it in. You have a freedom if you have an open surface. If you have an open surface, you can point in this way, that way. No limitations. All right, so the angle is going to be 0 degrees, but anyway, it's constant. And what happens to the area? Increases, right? So it's essentially this area of the loop, of course, it increases, right? So, of course, so now, as a result, we can say that magnetic flux increases as well. Increases in time. So Lenz rule over here. So increases, it means that our loop is going to rebel, behaves like Che Guevara, right? Come on, who is the most famous rebel in the world? Of course, Che Guevara, of course, right? One of those Cuban leaders of the revolution, right? All right. At least I didn't have a T-shirt with his face on that. All right. I was not a student in 70s. All right. Okay. So now it means that induced magnetic field is going to be in the direction opposite to the direction of the external magnetic field. Right. Okay. So now I can draw a bunch of what crosses within the loop. Dots. External, our opposite, so I can draw a bunch of crosses. So that's B induced. Great. So now we see the direction of the induced current, which is produced by the direction of the induced field, which is produced by the induced current, and directions of those two are connected, right? So cross, it's away from us, so it means like this. And my thumb gives me direction of the induced current. It means that clockwise direction. Am I right? Yeah, clockwise direction. Yeah. It doesn't matter where you apply, here or here or here, right? So every time you will get exactly the same direction. Yeah, basically like grabbing the loop, right, on one side. So it will be I induced or over here, I induced or over there, right? So same. So CW. Great, so now we know the direction. Now the magnitude. So now I will put a new bullet instead of that. So now magnitude. So now we need to grab Faraday's law and start applying it. Also, at the same time, I teach classical mechanics up undergraduate level, so sometimes it's. EMF. We need to start with EMF, and then we can make a transition to current at the correct point. And of course, I'm going to put the sign of an absolute value, because we already found the direction of the current, CW. So now, and that minus is responsible for the direction. So now we can drop that minus because we found the direction. All right. Okay. So now I can write it as, should I do it? Yeah, why not? So d over dt, and flux, it's a external magnetic field times area times cosine of, I just write explicitly the expression for the flux. It's a dot product. And the angle we already picked essentially, right? Over here. It's a 0 degrees, right? We picked the direction of the area vector, so it means that 0 degrees. Actually, it's not that big a deal, even if you have pi, we have an absolute value sign on top. Whenever you have an open surface, and this is an open surface, you have universal, constitutional, whatever freedom to pick the direction of the area vector you want. It must be perpendicular, but perpendicular, it can be this way, or it can be that way. You have freedom, no limitations. So for the closed surfaces, for the Gauss's law, we applied some limitations, conventions, right? So, but for the open surface, it's up to you. So in this case, this is my loop, and I decided to pick my area vector out in the direction of the external magnetic field, just to make the angle 0, for the sake of convenience. If you pick it into the loop, bigger deal, your angle will be pi, but anyway, so it's not going to change anything because we have an absolute sign of an absolute value. But still, I prefer to pick a certain direction and follow that direction. Make sense? Again, it's an open surface. I remember at some point mastering physics tried to apply some restrictions in terms of the direction of the area vector. I wrote big letter to them, guys. It's illegal, and they changed. they agreed. Okay, so now, of course, it will be as a result just a d over dt, external magnetic. You know what? Probably, yeah. Let me simplify immediately. So what can be done with the external magnetic field in this mathematically?
Oh,
It's constant. We can drag it out of the sign of differentiation and even outside of the sign of absolute value because it's a magnitude of the magnetic field. It's only positive number, right? So let's just extract it immediately. B external and absolute value of d over dt. And area. Area is a complicated, right? So and you know what? Let me label the area. Let me label it with, for example, these points. No, this point A, B. You know what B? Okay, you understand. It's a point B. A, B, C, D, and E. So the area consists of A, B, C, D, E, right? And I can divide it by 2. So first, the area of this rectangle and the area of that triangle, right? Which area out of these 2 actually changes in time as we drag the rod? Of course, the rectangle only. So over here, I can write the area of let me write. So it's area of A, B, C, E. And you know what? Let me erase this because it's now, I feel like I need that space. I need to invade this territory. Plus area of the triangle CDE. And we differentiate them with respect to time, right? You just now said that this is constant. What happens to the constant if you differentiate it? It will be 0. So that triangular area doesn't contribute anything. That's why I added it just for fun in order to make some changes. But essentially, that this appendix, of course, assuming that you are not with this triangular crossing, this crossing, no, it's everywhere. Pretty much there is no magnetic, the end of the magnetic field. So of course, these, or maybe which way I wrote it. So this will give us, okay, let me write, so dA over dt, this CdE equals to 0 because it's constant. It's constant. This will give us essentially 0. Okay, so now as a result, we're getting B external and the area of that rectangle ABCE. Okay, so now it's back to the classical example, which is discussed in every book when the rod is just straight. Again, I just modulated, let's call it this way, for fun. So this is the aerial velocity, how fast this rectangle changes in time, aerial velocity. But the aerial velocity is not given, linear velocity is given. And at this point, we need to apply just simple trick. Right. Usually I suggest, what if we introduce this distance? X. From the end to this line. Okay, so let me open my explanation box and write, let me introduce X. As a result, what will be the area, expression for the area? Lx. Again, every time I want to pronounce an Lx, it reminds me of what? LX 350, LX, Lexus, right? The car. Such a weird associations. L times X. I just used to watch one channel of one guy who reviewed the Lexus cars. Kind of fun. Okay. So B external and d over dt Lx. So now pure mathematics next. What can be done with L? The same story, just drag it outside of the sign of differentiation, right? Because L is constant, X is not constant, X is increasing, X is changing. So B external times L, and that's an ugly symbol, dx over dt. Dx over dt, it's our velocity, right? Just our linear velocity. So that's just a kind of smooth transition from the aerial velocity to the linear velocity. I remember, like, somewhere in the summer class about 8 years ago, I had a student. Now he works at Lincoln Lab at MIT. And with a problem like this on the final exam, he got stuck, and he was such a perfectionist. I remember he was sort of sitting angry, right? So he forgot how to handle this. But then after like 15, 20 years, like, oh, minutes, 20 years. So he realized and he passed it. And of course, he got his A, whatever. No troubles. All right, so BLV. Right. Very often, if we give problems like this, quite often students tend to just write immediately. It's kind of easy to remember, like QVB, BLV, right? We will never accept that, right? So again, we only expect from you to remember fundamental equations. Come on, it's not a fundamental equation. It's just something which appears after some manipulations, right? So we expect from you to start with the Faraday's law very quickly, of course, go through this, right? So extract, right? So and get to this BLV. If you just write BLV, no, we expect that students should, who works in science, should remember some set of fundamental ideas, and then the rest. That's why we have mathematics and calculus in order to get all these. Yeah.
Why do we take the absolute value?
Because at the very beginning, right? So we already, that minus sign just indicates the direction of the current. But we already found direction of the current, right? So, of course, when we're trying to find EMF, but it's the same direction of EMF and direction of currents are the same. So that was the logic why I put the sign of an absolute value, because we already found direction of the current. Minus is responsible for the direction. Okay, so of course you can plug numbers, you can calculate. I don't think, actually I did calculate. Wow, I'm so surprised. Usually I don't like plugging numbers. So you will get 0.3 volts. Numbers are given. Okay, and so now the value of the current, we're going to assume that at this particular moment, we know the resistance. Let's make that assumption. Of course, the resistance is changing with time, right? Because the more wire gets involved, right? But it's not a big deal. So now I induced equals to EMF over R. We're just training ourselves for how to handle physics. So EMF over R, I think I assumed 0.1 ohm. Let me write, assume R equals to 0.1 ohms. So 0.3 divided by 0.1, it will be 3 amps of current. Okay. Again, it's a typical U-shaped rail problem, but just for fun, just add a triangle. Right. I'm sure that lots of students would disagree that it's fun. Yeah. Because again, it's ubiquitous. You open any book and you can see this example. So I decided to add something. At some point, instead of triangle, I had some curve, some part of the circle. Even in the shape of the heart, we'll still just chop it, and only the rectangular part would contribute. Okay, enough. Any questions about this? You know what? What if, for example, just for fun, what if I assume that this is the edge of the magnetic field? And what if we take this rod and pass this edge of the magnetic field? So this U-shaped rail goes to infinity, let's say. And now the rod is somewhere over here, outside of the area of the magnetic field. What can you say about the induced current in that case?
It will stop, right? Once you pass that magnetic field.
So now we're talking about this situation. So let me just. So magnetic field up to this point, right? So this is a magnetic field, what dots, 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 dots. And now our rod is here. And we're still dragging it with velocity v. Again, you need to very quickly in your head, what happens to the magnetic flux? Because that's the every time we dance from the point of the flux. We come to the point, what happens to the flux, and then if flux is constant, nothing happens. If flux increases, this direction, if flux decreases, that direction of the current. So if we pass the region of the magnetic field and the rod is over here, what happens to the magnetic flux? We still have a closed loop. You see this closed loop. But what's the story with the flux in terms of time? No, flux is a number. It's the question: is it changing? Is it does it change? Is it changing or is it constant?
The area is still expanding.
Area increases, right? But flux. What is flux? What else except area must be involved? Of course, magnetic field.
Magnetic field, yeah.
Where is the magnetic field?
Only half of it.
Magnetic field is all the way there.
So magnetic
Okay, you can divide. Over here, of course, there will be some value of the magnetic field. Does it change in time? It stays constant. Of course, you're increasing area, but this area, does it contribute to your flux?
No.
Because there's no magnetic field. So as a result, yeah, area increases, but this part which increases area, it doesn't contribute anything to the value of the magnetic flux. Magnetic flux is only here, and it's constant. As a result, overall flux stays the same, constant. As a result, are we going to see anything? Of course, nothing. So yeah, if there is a borderline, then of course you need to look carefully what happens. But in this case, I think it's usually kind of everyone expects that if you know idea of the flux, and by looking, you should be able to come up with that that conclusion, because in this case, only this area contributes to the flux, and it's constant. Okay, so just some extension. Whew, so what's left? Inductance and modified Lenz rule, right? Lots of troubles usually with the modified Lenz rule. Then we will very quickly solve. You know what? Maybe let's discuss inductance. Then electromagnetic wave, and very quickly interference. Right? So like three problems. Okay, let me erase this, and maybe I will write it over here. So inductors, we introduce it much later for a very good reason, because in order to explain the work of an inductor, especially production of the potential difference across the inductor, you need to know Faraday's law. So we waited until we introduced Faraday's law, and only then we could introduce the inductor so that we can explain its work. It works. It's work. Right? Okay. So the situation is this. So we derive this formula basically under certain conditions. What is an inductor? It's just a simple solenoid, right? Under certain conditions, you can generate potential difference across the inductor. So if current through the inductor constant, nothing happens. It's just a piece of wire. Right? But if you start increasing current, potential difference starts being produced in the inductor. If current through the inductor decreases, again, there will be potential difference produced. So whenever you set potential difference, it means the V final minus V initial. Which point do we consider as initial? Which point is the final? Direction of the original current. Let's say this is the inductor, and original current, which is produced maybe here by the battery, goes that way. So this current enters the solenoid over here, so that's the initial point. It exits over there, so that is the final point. So that's how we define final and initial point, direction of the original current. So delta V, it's a V final minus V initial. And it is equal to minus inductance times rate of change of the electric current, original electric current. Okay, and then, so essentially, as I said, it's a Faraday's law, right? And in the Faraday's law, we apply it for the loop, right? And every time when you discuss Lenz rule, we were talking about the flux, about the flux. Now, so the same Lenz rule can be applied for the inductor in order to find the direction of, in order to find the value of delta V, direction of the current, and so on. But in my class, I tried to apply Lenz rule directly. And in that case, you have to apply you have to make 8 or 9 steps. This step, this step, this step, and keep applying. It's too much, right? It's not very practical. But if you look at that Lenz rule properly, then you can see that if I cut these parts, I can easily connect this with that, and still I will get the final result correctly. Or maybe I can cut this also, editing. It's like when you make videos, right? Lots of editing. The same here. If you cut some parts, you can still connect what's left, reduce the size, and you can still get the final result correctly. So if you apply Lenz rule directly, it's tedious, not very practical. But if you do some editing, you can come up with what I usually call modified Lenz rule. So that you keep the same story about something is growing, system tries to rebel. Something is dying, system tries to support. But now we're not supporting or suppressing flux. In the case of an inductor, we're supporting or suppressing the original current which flows through the inductor. And now I create a very similar 3-step situation. So if original current flowing through the inductor increases, the inductor hates it. Inductor wants to keep current as constant as possible. If current is constant, we can say that the inductor is happy, is in nirvana, whatever. It's so. But if current increases, it starts rebelling. Oh, damn it, you're increasing current through me. I hate it. I will rebel you, right? So I will start driving the induced current in the direction opposite to the original current, trying to suppress the rate of growth of the original current. Of course, it will never be able to succeed completely, but it will reduce the rate of growth. right? And of course, usually, like in my classes, I usually ask at this point, so yeah, it's cool to be a rebel, right? So yeah, some people find it romantic, but where is the money in order to be a rebel? It's very, very expensive. And of course, in this case, so where's the energy to rebel or being supportive? And when we introduced the inductors, I told you that it's a device which allows us to store energy in the form of the magnetic field. Inside of the inductor, there's some magnetic field, so it means that some energy is stored, and that energy can be used to suppress or support, to have that fun, right? But of course, it's limited amount of energy. So if current increases, it rebels, induced current in the direction of opposite. And then once you know the direction of the induced current, because you know the direction of the original current usually given. So now you know the direction of this. And then you know that every time current flows from plus to minus, from higher points with the high electric potential to the points with lower electric potential, you can get information about delta V. We will look at the example. So then if current is original dying, the inductor, damn it, I don't like it again. So, but now the response will be absolutely different. So now it becomes supportive. It will start driving the induced current using internal energy in the current in the direction, the same direction as the original current. And then once you know direction of the induced current, and you know that every time current must flow from plus to minus, you can arrange which points is at higher potential and which points is at lower potential. Okay, so let's look at the example. Here in my notes, I discussed more, but probably I'll skip. You can look at by yourself. And over here, basically, I wrote that. Right? Now, let's look at the example. So let me write. So it's a number. Okay, let's call it number 9. And these are inductors. Okay, so let's assume that we have this situation. Over here, there is an inductor. This is the symbol for the inductor. Then there is a battery. Right. Okay. And so battery drives the original current, which creates all this mess. So what's the direction of the original current? Counterclockwise, right? Original current. You see here we have plus, here minus. Of course, original current is going to flow that way. So of course here plus. You know what? Let me use blue. Let me use blue and red for the induced. So this is plus and minus. So as a result, the original current flows this way. I know. And increasing. And let's assume that we know it increases. It's given. Now, I label these points. For example, this point is what? A. And this point is B. So now my question is, what can you say about the electric potential at point A and point B? And I'm talking about the electric potential produced by what? Solenoid. So they're like produced by solenoid, produced in solenoid, like produced, made in USA, made in China, made in what, Vietnam, made in solenoid. Again, using that internal energy. So pretty much every time you need to remember, it's basically a battle of two potential differences. First, original potential difference, which is created by this battery. And then there will be some additional potential difference, which is produced by the solenoid using its own internal potential energy. Yeah. No, in this case, it doesn't matter. We're discussing just conceptually. We just want to connect all these directions of the original current, induced current, and the potential difference across the inductor. Sometimes this rule has to be applied in the opposite direction. Delta V is given, you come to this point, and then you need to jump to the conclusion what happens to the original current. So this rule works both ways. Right? So here, what is given, and now we need to answer the question. What can you say about the electric potential? Okay, let me write compare. VA and VB. Or you can say, so what's delta V, for example, right? So essentially the same, right? Okay, so we just need to apply this modified Lenz rule again, creating the story about original current. Increases, something happens. Decreases, something happens. Okay, so in our case, I naught increases. So immediately we start applying. So the inductor hates it. It doesn't like it. So in this case, it rebels. So it means that I induced must be in the direction opposite to the direction of the original current. Original current counterclockwise, so induced current must be clockwise. And again, remember, every time it starts on the ends of the inductor because that's the source of that induced current. So usually, every time that current, I starts on one end and ends on the other. So what the direction? This is counterclockwise. It should be clockwise. So clockwise, it means this way. Clockwise. It means that I need to draw something like this. You see, I started on one end, and because that's the source. Essentially, you can think of this inductor as a small battery. And in order to drive this current, here it should be positive electrode, and there should be negative electrode. Because every time any current from plus to minus, this induced current, let me write it's I induced. It also must flow from plus to minus. So it means that this point must be at higher potential. It's ugly plus. This point must be at higher potential, and that point must be at lower potential. Again, those potentials produced by the inductor, independent of that battery. Of course, battery is the source of the whole trouble. So plus minus, and that plus minus give us this direction of the induced current. So now we can say that the last step, it's about this delta V. So now we can get information. So V at point A is larger than V at point B. 3 steps every time. But now the story is about the current. And remember that current from plus to minus, but that's even if somebody wakes you up in the middle of the night, you will be able to answer that question. In other situation, I just try to come up on the fly. What if we have this situation? Let's say we have an inductor. Let's say this is the battery, right? Which drives an original current. Of course, you can say immediately the direction of the original current would be this way, I naught. But we don't know what happens to the original current. Somebody behind the wall is doing that, and we want to find out what happens. But let's say we have a voltmeter, and we can measure the response of the inductor. So something happens to the original current, and we see the response of the inductor. Let's say we see that, again, I'm just making it up. We see that, let me call this point, we see that over here we have plus and here minus. We see the response. So let's say this is point A and this is point B. So we see the response. So now we need to answer the question, what happens actually in time to this original current? So let me write what is given. So I naught, it's a CCW given. And we know that V at point B is larger than V at point A, also given. So we need to answer the question, what happens to the original current? Is it going down or up or constant? So that's essentially the question. We need to see what happens to the original current. Okay, so now essentially we just need to apply this rule, but in the reverse direction. Delta V is given. You need to see what will be the direction of the induced current relative to the original, and based on that picture, you can say what happens to the original current. Okay, so so delta V, since, okay, let me write what, VB is larger than VA. So what's the direction of the induced current? Clockwise? Okay, let me see. So from plus to minus, Ah, you said counterclockwise, right? Because I heard only clockwise in the first part.
Clockwise.
Huh?
I said clockwise, plus to minus, right?
That's the typical mistake. It's a typical mistake, right? So look, guys, this plus and this minus are produced here.
Oh.
And then current flows through the rest of the world. I usually, in order to explain, sometimes I try to reduce even the size so that students wouldn't have a desire to draw the current in the wrong direction. Or usually give this a comparison. Let's say you have a production line producing something, whatever, smartphones, or so whatever. Then, so that's the where plus and minus produced. And then you're not sending them back to disassemble, right? Sending them back, or sending to the rest of the world, right? So here, smartphones are produced, and then you send them to the rest of the world for the consumption, right? So the same here. These plus and minus are produced here. So that's something happens, and then, of course, current will be. It's a very, very typical mistake at the very beginning. Right? Mana, good? So it means that plus over there, minus over here. So, and you see every time I kind of start on one side and end on the other side. Of course, it's a loop, right? So you understand it goes through everything. So from plus to minus, so it's I induced. So I induced, it's direction, the same as the original, right? Both currents are the same. So the same current, it means that the original current is dying. The system becomes supportive. You see, directions are the same. Counterclockwise, and this is also counterclockwise. So from here, I can say, so I induced is in the same direction as I original. So as a result, original current is dying. So it's supportive system. System is supportive. Okay. So this conceptual, yes, can be a little bit confusing at the very beginning. But if a problem about just solving the value of finding a value of delta V, it's usually quite straightforward, right? So let's just solve quickly one example, one problem. Okay, I should be able to fit it here. So let's call it number 10, although it's pretty much under the same roof of the inductors. So there's an inductor. That's my I, capital I. Sometimes students ask, what the hell is that? Is it? In my high school days, it was in 80s. I had a book in calligraphy, and so I remember I was practicing a little bit. So these are these residues of this. So inductor, inductance is given L, 280 millihenry, H Henry. So current changes steadily. So initial current, let's say 25 amps, and then changes steadily. Steadily changes to I final, which is 10 amps. And that happens in the period of time, 360 milliseconds. We need to find the potential difference across the inductor. So maybe let me just quickly draw some pictures. So let's say this is the battery, which drives the original current. So this is our inductor, right? So that current, you see this current, what changes going down, right? So we need to find what happens to the potential difference. Numerically, actually, need to find delta V. So numbers are given, so the question is not conceptual. So essentially, we just need to grab the formula. Where is it? Here, delta V, for the potential difference across the inductor. and plug numbers. So in the problems of this type, they're quite trivial, just like a couple of minutes. Delta V. And again, where is final point and where is initial point? Because delta V, it's all the time V final minus V initial by definition. So original current exits the solenoid over here, so that's the final point. And of course, this is the initial point, right? You remember that convention. So it's a minus L and di over dt, rate of change of the original current. So this di over dt can be replaced with what? Changes steadily. Basically a linear dependence. No, zero. Delta I over delta t, because this is changes over infinitesimally short period of time, but it's not given. We have a changes over 360 milliseconds. And the problem says changes steadily. Thanks God, at least in this problem, there is an explanation. There is a that information, because very often problems just ignore that, assuming that yes, you just replace, right? So essentially it's a slope or where you use infinitesimally small change of time, but you will get the same slope if you use finite change in time if you have a linear function. yeah, because it's constant. So minus L delta I over delta t. That's kind of long. Delta I over delta t. Okay, so now we just need to plug numbers, nothing else. So problems of this type are quite straightforward. And again, as I said, it's said in the class. This idea is used to ignite the fuel in the engine, right? So there's a solenoid, sudden change in the current, and let's say you open the circuit, gigantic potential difference will be produced across the inductor, and there is a small gap, right? So, and of course, there's a spark produced. There will be spark produced, and that spark will ignite your fuel in the engine. So minus 0.28 Henry. I converted to Henry from millihenry. And then changes in current. Every time keep track which point is final, which current final, and which current is initial. Final is 10 amps minus 25 amps divided by 0.36 seconds. So I get rid of those prefixes. Oh, no way, I'm not going to calculate this. I'll just use my notes. Oh, actually, the numbers are quite nice. 12 volts only. Nice. So positive, it means that which point is at higher electric potential? Final points, right? So positive, so it means the final point. This point is at higher electric potential. Of course, you're analyzing this conceptually, you will end up with, of course, with the same answer. So usually no troubles with the problems this type. Okay. Let me, again, if something is, we can discuss. Next, I'm planning to very quickly one problem about electromagnetic waves. And usually students do quite well with those problems with the same amount of time spending discussing it, right? So don't panic, right? So it's of course there are lots of questions. Sometimes you feel like dizzy, right? So there are like 10 questions, right? Each worth like 2 points or 3 points. And of course, all those formulas are given. You just need to get used to this wave number. Of course, I got used because I've been working in optics for many years. Okay, good. All right. So electromagnetic wave, and that will be number 11. Okay, according to my counting. So EM wave. Whew, what is given? Frequency. So F equals to 60 hertz. Very low frequency. Of course, as a result, the wavelengths will be gigantic. But again, it's just an exercise, right? So in order to plug correct expressions. All right. So then, electromagnetic waves with this frequency propagates in plus z direction. It's given. And the amplitude of the electric field is given. E sub 0 equals to, what's the value? 2 volts per meter. And the electric field oscillates in, wait, which direction? X direction. Electric field, so E oscillates in X direction. I cannot say plus X or minus X because it will be, at some point, it will be in the positive X direction. Then next cycle, it will be half of the cycle, it will be negative X direction because every time electric field and magnetic field, they oscillate, right? Okay, let me draw the picture to make it clear. So it propagates in a Z direction. So this should be my Z. Then a right-handed coordinate system. Let's draw the right-handed coordinate system. So in order to get this direction, so this should be X. No, this should be X. This should be Y. Cross product of X and Y must give you plus Z. That's the basic definition of the right-hand rule. Cross product of X and Y should give you Z direction, positive Z direction. So it means that this is X, this is Y. Let me confirm. Yeah. Okay, wave propagates that way. Electric field oscillates in the X direction. This is a transverse wave, so keep track of what are you talking about. Electric field oscillates in the X direction, but the wave propagates in the Z direction. It's like a wave on the chord, points moving up and down, and the wave propagates in the perpendicular direction. It's a transverse wave, right? So because this is the one of the major places for mistakes, right? So students get confused, right, with in solving problems. Of course, wrong directions are shown: direction of propagation and direction of oscillation. Okay, electric field oscillates in X direction. So, and let me use sine function. Yeah, not cosine, although it doesn't, it's not really matter. So that's my X. Electric field, not X. Electric field in the X direction. So you see, sometimes it's in the positive X direction, then over some period of time, negative X direction. That's why I wrote just in the X direction. And of course, it propagates. So speed of the wave is that way in a Z direction. Transverse wave. Then, in which direction does the magnetic field oscillates? Yeah. Every time electromagnetic wave, in the electromagnetic wave, these three directions, direction of the electric field, magnetic field, and velocity, they are perpendicular all the time to each other. That's the intrinsic property of the electromagnetic wave. So if you know this is direction of propagation, speed, direction of the velocity, and if you know this is direction for the electric field, magnetic field must be in the last available direction. In this case, direction of the Y, direction of Y. Right? So every time E, B, and V, velocity perpendicular, mutually perpendicular. Yeah. Not the shape, deeper. Meaning deeper, not just the shape. They oscillate in unison, right? Or I compare it with the happiest couple on the face of the universe because they share ups and downs all the time. They never give up, never quit, so forever together, regenerate each other, right? So according to the Faraday's law and Ampere Maxwell's law, right? So it's the happiest couple on the face of the earth, right? Example of the true love. I was just joking in the class. Okay, they know. So something like this. My attempt to draw a three-dimensional picture. So this will be my magnetic field, our magnetic field. So that's B, and that's E. I prefer usually to sketch it to make sure that I don't make any mistakes. But of course, imagination is enough in order to imagine it easily. Okay, so that's just a, and you see all the time perpendicular. Let me write. So it's a E perpendicular to B and perpendicular to direction of the velocity. And actually, cross product of E cross B must give you V direction. It's a pointing vector, but we didn't introduce it in this course. Direction of which energy propagates. Okay, so now what needs to be found? Frequency is given, amplitude of the electric field is given. So I want to write mathematical expressions for the electric field traveling wave and for the magnetic field traveling wave. That essentially something like this. Over here I wrote. Essentially, I just want to write these mathematical expressions for the electric field and for the magnetic field. Because that's what we need. If you know that, you can say that you know everything about that or this wave. Right? So in order to find this, okay, let me first rewrite it. And no, I don't want. I want to save that for the last discussion. So we need to find amplitude of the electric field is given. So we need to find K, wave number. We need to find omega, angular frequency. We're going to assume that the initial phase is 0. We're going to make, and I usually make that statement in the problem, so because that sometimes can be difficult to find, or in optics because the frequency is much, much larger. Most of the time, we don't care about the initial phase, right, of the wave, right? Unless it's a very, very low frequency oscillations, then of course it might be important. Okay, so now let's find. First, we will have to find, let's find K and omega. So that's kind of semi-global goal. And first, let's find the, let's say, wavelength. Maybe, let me write. So VW/length. Okay, so wavelength. You remember in your lab class, instructors what kept telling you, so these are temporal quantities, these are spatial quantities. I push them, guys emphasize on that. Wavelength, spatial or temporal quantity? Spatial, it's basically distance over which wave reproduces itself. This is essentially a snapshot graph, essentially the photograph of the wave, if we could take a picture of this electromagnetic wave. So essentially, this is wavelength, our spatial quantity. We don't have any special information right now. Frequency is given. Frequency is temporal information. So we have information temporal. So how can we usually make a transition from temporal quantities to spatial quantities, or from the temporal world to the world of to the spatial world? There is one parameter which works essentially as a bridge between the world of temporal quantities and the world of spatial quantities. Velocity, why not very confident? You remember how do we usually find speed in physics 1? You take the distance, which is spatial quantity, and divide it by the time, which is temporal quantity. So you need to juggle both spatial and temporal quantities in order to find the speed. So essentially, speed or velocity works essentially as a bridge between the spatial quantities and temporal quantities. So if the problem gives you only, let's say, temporal quantities and you want to find spatial, most likely you need to jump through the bridge through this velocity in order to make this transition. Or if spatial quantities are given and you want to find temporal, again, most likely you'll have to use the speed. And do we know the speed? That's a typical problem on the exam. Sometimes even good students sitting kind of, where is the speed? And I would walking around telling, guys, everyone knows, and you know, and toddlers know that quantity. And then after 10, 15 minutes, they should, now I know, right? So it happens, yeah. It's the speed of light. Whenever you see an electromagnetic wave, immediately it should trigger your brain. I would never give you, I would never tell you, right? So those facts, like, it should be already in your blood, right? So. No, frequency domain essentially is a temporal domain. Of course, it's a temporal domain, right? What do you mean inverting temporal? You invert, if you want invert frequency, you will get a period. It's still the same domain, right? It's still temporal. It's a temporal world, right? So, it's in terms of practical work in the lab. All right. So it depends on which equipment you have. Like, for example, if you work you have only oscilloscopes available to you, right? So, and you want to analyze some behavior of the system, oscillating system, you can get only temporal information, because that's what you see on your oscilloscope, what dependence of some quantity on time. So temporal, of course, you are doomed to work in the time domain. Right, time domain. But if you have a spectrometer, spectrum analyzers, whatever, they give you basically frequency information about the frequency, then you can say that, yeah, you are in the frequency domain, right? But of course, they kind of, what you said, inverting, but again, it's basically temporal time domain or frequency domain is basically in terms of applications, depend in terms of which equipment available for your work. In this case, we're dividing these two worlds because the wave lives in time, the wave lives in space, and so that's why I'm blabbing, and now I'm starting. Yeah. You will still have to go through the speed of light. Yeah. So pretty much you still need to jump over that bridge or walk over that bridge. Okay, not jump. All right. Yeah, we have to be careful. Okay. Yeah. So we need to find what? Wavelength. So we just need to grab the formula for the speed of velocity. Where is that? Yeah. V equals lambda f. Right? So V, which is c speed of light, it's lambda times f. So essentially a bridge. And of course, velocity is neither temporal nor spatial quantity. So lambda equals to c over f. So 3 times 10 to the power of 8 meters per second divided by, frequency is so low, ridiculously low. But again, it's real. It's possible. All right. So of course, it will be a gigantic number. I will let me write 5 times 10 to the power, just an exercise, right? So I'm even afraid to pronounce that wavelength. It's a huge, right? You can imagine, right? So, all right, not very realistic, although, yeah, why not? So now, can we find the wave number? Wave number, it's a spatial frequency, essentially physical meaning. So what is that? Essentially, you take, let's say, 1 meter, and it tells you how many wavelengths you can fit in 1 meter, how many cycles you can fit in 1 meter. Angular frequencies, you take 1 second and see how many cycles you can fit in 1 second. Basically, omega and k is the same kind of ideological meaning, but that's over 1 meter, that is over 1 second. Right? So how many cycles you can fit. Right? Okay, so k, by definition, wave number, 2 pi over lambda. That's how we introduce it, 2 pi over lambda, wave number. So maybe let me write underneath, it's a wave number. Okay, so everything is given. 2 pi divided by 5 times 10 to the power of 6 meters. And again, the number will be ridiculously small. 1.26 times 10 to the power of minus 6. Inverse meters, inverse centimeters. Of course, radians is kind of over there, but I don't know what's the reason. We never usually pronounce radians per meter. It's just inverse meters, inverse centimeters. But whenever people talk about angular frequency, every time radians per second, radians per second. I don't know, I can't explain why is that. Anyway, so meters to the power of minus 1, inverse meters. Okay, so that will be over here. Okay, so now let's find omega. ABC, so omega. Again, by definition, it's a 2 pi over t. You see the same, k and omega, sort of the same ideological meaning. But that is in time domain, that is the, okay, now not domain, time, spatial world and temporal world. That's how I usually. And of course, 1 over t, it's a frequency, right? Frequency, it's not this. This is angular frequency, that is just regular frequency. So it will be 2 pi f. F is given, F is given. It's 60 hertz. So it will be 120 pi. Again, don't be afraid to leave your answer in terms of pi. It's absolutely legitimate. Okay, so now we can write down the mathematical expression for the electric field and for the magnetic field. Oh no, for the electric field. So A, B, C, D. All right, so E will be equal to E naught, amplitude, which is given. And let's say, yeah, let's use sine. Sometimes if you see cosine function, don't panic. Come on, it's just initial phase is pi over 2. So, and k, which variable must be used next to k? And then, of course, there will be some sine, and then there will be omega t. We're going to assume that initial phase is 0. Let me write, assume. I don't care about that initial phase. So now you see gaps. Which variable must be used here? You think Z. Z? Just agreeing, or you see it? I know you guys can be very agreeable. Okay, what can you say about this x in this formula? It's a direction of what? Of course, it's the direction of x. I agree with that. But what happens along that direction? Propagation, wave propagation. It's a direction of wave propagation. And you're absolutely correct. Wave propagates along which axis? Z. It must be Z over there. That's the place for lots of mistakes. Students just keep writing whatever. Most of the time, usually X, yeah, because that's what is given in the formula sheet. But no, you need to have a clear understanding what's the role of that particular variable. So here must be Z. Direction of wave propagation. Then what should be over here as a subscript? Sometimes unit vectors is used. I usually prefer to use subscript. Which subscript must be used? Okay, I see your confidence. Okay. X. Ellie, agree? Of course, you're together. X? Yeah, of course, it's a direction along which E oscillates, electric field oscillates. Again, keep direction of oscillation and direction of propagation. That in this case are different because it's a transverse wave, X. And again, this point and that point, that's lots of mistakes. Although it's, again, it's shouldn't be. Then, plus or minus. Yeah, we need to remember that reversing situation. If wave propagates in the positive, let's say, Z direction, over here, there must be minus. Again, it can be derived, it can be shown, right? So, and I asked you to read that my notes. So, reversing situation, we need to remember that. So, essentially, this place for mistakes, this place for mistakes, and this usually place for lots of mistakes. These 3 spots. Almost every year. Otherwise, here it's quite often. And of course, don't forget about units, right? So don't just generate numbers, right? It's good to generate numbers, but also you need to show what you found, right? Okay, so now magnetic field. What else do we need to find in order to write down a similar expression for the magnetic field? What else is still missing? B naught. Another place, very often students, when I ask write down expression for the magnetic field, they just look. Oh, there is an amplitude, just grab this and start. Of course it's wrong. Come on. It's electric field amplitude, right? It has nothing to do. So, D, E. Okay, so let's first find the magnetic field amplitude. And it is connected to the electric field amplitude directly through the speed of light. And the electric field way larger than magnetic field amplitude. Speed of light, 8 orders of magnitude. I cannot imagine that. It's a huge difference, right? More than huge. So it's a E naught divided by C. Again, this formula is given in the formula sheet because we did not derive them. Of course, it can be done, but it's very tedious derivation when you have to make a transition from the Maxwell's equations to the traveling wave equation, that second order partial differential equation, which we just discussed in the class. I did it once in my first semester in 2014, and students were really shocked, right, looking at that. I just followed the book, right? But since you're not physics majors, so I decided it's not worth of trouble. Anyway, so again, it's given in the formula sheet, just find it. So 2, of course, volts per meters divided by, yeah, of course, I know the speed of light. I don't need to look it up. No, I will just look. My brain started shutting down occasionally. Minus 9 units. Of course, you can try to analyze units, but no, I would never do it. Of course, yeah, just remember units of magnetic field Tesla. It's named after the guy, not after the damn car. So I explained my sentiment to students in my class, right? Because it basically shadowed completely the Nikola Tesla, right, guy. As a scientist, I find it very offensive for him. He was a great guy, Nikola Tesla, and now it's all car. All right, okay, so now, of course, I can write expression for the magnetic field. Subscript. Who said Z? Don't listen. You see, it's try to be a saboteur, right? Why? Right? Yeah, of course, in the y direction, magnetic field. So you see, that's why very often I prefer very quickly sketch the picture so that I wouldn't make some silly mistakes, right? So when you just feel overly confident, that's why. By. So equals to, of course, B naught. I'm not going to write it. We found it. And then the rest. What is the rest? Do we have to invent something new? It just. Oh, God, no. You remember, again, I usually, it's the happiest, they oscillates in unison. Every time they share ups and downs, they are excited together, they feel like depressed together, right? So feel like zero together, it's all late. So pretty much you just copy and paste. Grab these x and time dependence exactly the same and rewrite it over here. So only, of course, symbol of the field and the subscript different. And of course, amplitudes are different, but x and time, space and time dependence exactly the same. Just copy and paste, right? Okay. And you see on the picture, you see they are in unison, absolutely. So sine kx, you didn't see it? Force of habit, because most of the time we write that. Kz minus omega t. And of course, initial phase, I usually dump it, unless I ask if, but usually I don't do it. And in this semester, we didn't solve the problems about how to find that initial phase. Again, it's not that complicated, just a little bit of mathematics. Right. Okay. So again, there is no reason to be afraid of these problems. Again, the students do reasonably well, and it's sort of like this. Again, a little bit tedious because there will be like 10 questions. Right? And don't forget about the units. Very often students just kind of keep generating numbers and keep skipping units. And of course, we are as nasty. Start subtracting points for that because you need to follow. You need to explain people what you found. So the last, right? Yeah, actually, it's only 3 hours, 20 minutes. Yeah, it's still good. The record I told in the previous exam review sessions, my record was 4.5 hours for the final exam review session, but it was like a few years ago. All right. No. Now it's kind of now I remove some problems you feel like they're overlapping, right? So just try to optimize it. Okay. I'm not in the mood of breaking records because tomorrow I will be collapsing. I will collapse and sleep half of the day. Actually, quite often after the exam review session, I feel like. I still need to grade classical mechanics homeworks. Okay, so you know what now? Let me erase this as well. So number 12, interference. So usually two types of waves I give. It's either acoustic or electromagnetic. Of course, whenever I give an electromagnetic waves, I don't give the speed. Right? So you remember the speed of light. Of course, acoustic I have to give you because acoustic wave depends on the temperature of the environment. So that must be given. Right? So two speakers. And I should have written over here, in-phase speakers. Of course, you understand immediately, right? So it should bring some memories. Okay. 2 meters apart. You know what? Let me draw the picture. Let me start with the picture, then it will be easier to. So these are speakers, speaker number 1, speaker number 2. They must generate the same waves. Initial phase can be different, but in terms of frequency, in terms of, life in space and time must be the same because we derive the conditions for two identical waves. Identical sources and identical waves, they're kind of slightly different things, right? So frequency is the same. So F equals to 700 hertz. I don't know which note is that, or if you're musicians, you might know. I have no idea. So, but it's acoustic, huh? High pitch? I'm not. Okay, then speed. Okay, that dot must be removed. 341 meters per second. Okay, the rest of the geometry, let me show it on the picture. So the distance between these two speakers, 2 meters. Let me draw this center line. All right, so it's a center. This distance is 1 meter. This distance is also 1 meter. Okay, you know what, before I continue with the geometry, so essentially where are the waves? So this creates, of course, a spherical wave, but we're going to look essentially at the cross section we can draw as a circular waves. So let's say this blue will generate something like this, right? So these are, how do we call these lines? Kind of military fronts. Huh? No, maybe at in some fields it can be called like this. Wavefronts. So wavefronts. So these lines are, and what's so special about the wavefronts? Which peaks? Okay, crests. Yeah, crest, peaks, whatever. It's so these are wavefronts, and then of course the second. Let me use blue. I mean green. Right. So two identical waves overlap. Of course, they're going to interfere. You can pick any point and ask, are we going to see constructive or destructive interference? Or maybe something in between. And of course, this whole area will be filled with constructive, then destructive, then constructive, destructive, constructive, destructive. Pretty much it's an infinite number of points of constructive or destructive interference. Constructive amplitude is doubled. Let's say this is, 1 meter amplitude. Then doubling it will be 2 meters. Destructive interference, nothing. Then again, 2 meters. Then again, nothing. Right? And of course, between them, there will be kind of smooth transition. Something in between. So the problem asks for this particular point, which is, okay, let me draw another line over here, right in front. Then from this to that, it will be, so this is 1 meter, this is also 1 meter, so this distance is 2 meters. Okay, you see the central line here, 1 meter and 1 meter from the central line, and from this central line to the point in question, which we want to discuss, is 2 meters. So this is the point where I know somebody is standing and listening, right? Acoustic waves. So the question is, he going to hear something loud, maximum loud, very loud, or just a noise, acoustic noise, right? So we can call it point P. So we need to discuss at point P. So what are we going to see? Constructive or destructive or something in between, or in between. We need to analyze. Another thing which I forgot. The distance from this plane in which speakers are and to the point of the guy, 5 meters. This distance is 5 meters. So let me draw this line. And this is 5 meters. Okay, that's it. Nothing else. Frequency I wrote. Yeah. Okay. So, of course, we spend tons of time deriving the conditions, kind of tedious, but solving problems is almost like this. Just need to grab the conditions, find 3 parameters, and analyze. Conditions are over here. And of course, they are given on the formula sheet. Again, we spent like 40 minutes deriving them, and you were confused. Yeah, I remember. So let me write these conditions. Delta phi equals to 2 pi over lambda, it's essentially a wave number. Then times the path length difference. Essentially, it's a difference in the distances that waves must to cover on the way to the point in question. Delta R. In plus that infamous inherent phase difference, which usually confuses people, students quite often. But you just need to read the problem correctly. Interpret the words of the problem correctly. And then if you get, of course, you will calculate this, add them up. If you end up with integer times 2 pi, then immediately you can say that at that point, there is a constructive interference. If you have integer plus 1 over 2 times 2 pi, so that's the condition for destructive interference. That's it. So pretty much everything, the whole problem is over here, nothing else. So I usually start with the inherent phase difference. Even from the word inherent, it means what? It's basically initial phase of this wave minus initial phase it's that. Minus initial phase that. And since these initial phases are the same for this wave and then for that wave, so it means that it doesn't matter which point you pick the inherent phase difference will be exactly the same. If you move yourself, for example, from this point to that point and try to solve the same question, answer the same question, the inherent phase difference will be still the same. You move yourself over here, delta phi naught will be still the same. That's why it's called inherent. So it's pretty much property of the whole system. So in our case, what can you say? Okay, let me write. So inherent phase difference. Just a little bit left, maybe like 10 minutes, maybe less. Inherent phase difference. Delta phi naught. And okay, do you remember how to get information about the inherent phase difference? Why? Agree? You just need to read it from the problem, from the statement of the problem. Usually it's given. So if a problem says two in-phase sources, in phase it's immediately identical sources essentially, or identical sometimes words are used. Inherent phase difference is 0. So it means that initial phases are the same. Or if it says two out of phase sources, of course that means pi. Inherent phase difference will be pi. So yeah, just basically, or sometimes I can, at some point I used to give it, let's say I gave explicitly initial phase over here, let's say 3 pi over 2 and here pi over 2, right? So then how to find the inherent phase difference? Just subtract them, right? So come on, it's a banal story. So it's either initial phases are given or from the text. So in this case, it's a 0 in phase sources. Okay, speakers. And lots of troubles at this point. Maybe the only explanations, maybe students just don't listen though, or don't come to classes sometimes, right? Because I just need to remember. So the path length difference now. So now we know delta phi naught. So now path length difference. Path length difference. Marker started losing the contrast, but still good enough. Path length difference, delta R. So that's first bullet. Now the second bullet. So delta R. So it's a R2 minus R1, pure geometry. You see geometry. So R1, it's a distance. Okay, let me call it. This is the first speaker. This is the second speaker. So this will be my R2 from the source to the point in question. And then R1, it's this. Just a bunch of, okay, two Pythagorean theorems must be applied twice. Right, so let me draw this line. So R2, it will be what? This is 5, right? And then this is 1, and then 2, so it will be 3. 5 and 3. You see, for R2. So it will be R2 equals to square root of 5 meters squared plus 3, right? So it's a 2 plus 1, yeah. 3 meters squared. Sometimes, okay, guys, I'm warning. Sometimes when you prepare the problem for the exam, so it's so difficult to get exactly, let's say, integer number of. So if you very, very close around it and come to the conclusion, it's a constructive, because sometimes students, it's slightly off, it's not exactly, it's difficult to get exactly the same, exactly integer, for example, let's say. So. Wait, no way, I'm not going to. Hold it. It's a 25 plus, no, it will be 34. No, so I will just use my notes. So it will be 5.83 meters. Okay, so I usually keep slightly more sig figs. 5.83 meters. And then R1. Okay, R1. Again, it's a 5, and plus 1 only. Because this is 2, this is 1, so that will be 1. Right? So 5 meters squared plus 1 meter squared. So it will be square root of 26. No way. 5.1. So delta R will be 0.73. Right, so delta R will be 0.73 meters, so the difference. Okay, so what else we need to find? Wavelengths. We have frequency, wavelengths is not given, right? You see this denominator. Right, so the last element, so ingredient. Speed of light. Although I saw in the exam sometimes students speed of light for acoustic waves, right? So yeah, it happens, right? So of course it's not cool. All right, so 341 meters per second, and again, it doesn't happen often, but I've seen it. Divided by where is my frequency? 700. 700 hertz. It's 1/seconds. Right. So seconds will be cancelled. So we'll get meters. Oy, these numbers are not nice. So you will get 0.486 meters. Okay. So now we have all ingredients. Now let's just drop them in the same condition. So over here and see what we're going to get. Okay. So delta phi equals 2 pi divided by wavelengths, 0.486 meters. I'm just plugging numbers in the condition, nothing. Divided times delta R times 0.73. In plus, inherent phase difference is 0. So not exactly, but close to what it's. I think it's a 3/2. This is close to 3/2. So you're going to get very, very close to 3 pi. Constructive, destructive? No, you here is that everything is in front of you. We just need to, we got this number from here, and now we just need to see, are we getting this, because m integer, you remember, it's a 0, 1, 2, 3, and so on. That's what m is. So we just need to see, are we going to get, can we get this number using this condition or that condition? That's it, for all possible m's. You just see, can I get it with m equals 0, with m equals 1, with m equals 2, so, constructive? Constructive, right? What? Constructive? Yeah. Yeah, it's very, girls, what? Destructive, right? Yeah, usually in the classes, yeah, at this point, very often students go with that. And I actually tried to explain, you remember, right? So what's the logic? But I was surprised in this semester in my section, everyone, no, you answered correctly. Okay, look, you thought about destructive. Destructive, hold it, you said destructive or constructive? Constructive, it's an integer times 2. You understood, right? If you take any integer and multiply by 2, which number are you going to get, even or odd? Even, of course, you will get an even number. We have an odd number. It's impossible out of this get an odd number of pi's. Out of this, you can get only even number of pi's, right? So yeah, it's a very, very common at the very beginning, but I was quite surprised in this semester in my section, everyone, no, they answered it correctly. It's not very typical, right? So I was quite pleased. So, but still, yeah, very often why people pick constructive, because it feels like their logic, it looks like it's simple, and out of these conditions, this is simple. This is kind of complicated, and they jump to the wrong conclusion. Right, so you need to dive a little bit deeper, right? So then, right. Okay. So now, but still, we need to compare. I mean, we need to analyze this and see. What are you saying?
Naturally, people look for like half of something.
Yes, but still, right? So you already you develop the habit of analyzing it that way, right? So, but okay. So now let's still check the destructive interference. So which integer is going to give us this? 0 will give us just pi. It's not pi. You see, m equals 0. M equals 1. It will be 2 over 2 plus 1 over 2. It will be 3 over 2. Times 2 pi, it will be 3 pi. So it's a 4m equals 1, right? It's for m equals 1. So this is for m equals 1. Of course, if you step away, you will get for m equals 2. Then there'll be somewhere in nearby for m. Yeah, it's destructive interference. Yeah. So pretty much that guy is going to hear nothing but the noise, right? Or ringing in his ears, right? Okay, so that's and usually no, it's not significant trouble, no significant trouble. So over here, except for